And for more NASA videos, hit subscribe.
Europa is widely considered the most likely place in our solar system beyond Earth to have life right now.
It's a moon, an icy world orbiting Jupiter.
Beneath its icy surface, a global ocean of water. Everywhere on Earth that there's water, there's life. So we want to understand, could Europa be a place where life might exist today?
3, 2, 1, lift off.
Europa Clipper is the first mission dedicated to exploring Europa.
This is the largest interplanetary spacecraft NASA has ever built and launched.
We have the right team, the right technologies to leverage to go to Europa now and unlock those mysteries that are just waiting for us.
The pictures we're going to get from Europa Clipper are going to blow our minds.
How could you not be excited about something as monumental as this?
Welcome to NASA Science Live. Today, we're pulling back the curtain on one of the most exciting space missions of our time, Europa Clipper, a mission that will explore Jupiter's icy moon, revealing what's beneath its surface. I'm your host, Tahira Allen, and I am so excited to be here with you today. Now, here's the best part. Today isn't all about us talking, it's about you. If you have questions throughout the show, send them in using the hashtag AskNASA on social media or drop them directly into the comments wherever you're watching. Okay, let's jump right in. What makes this mission so special? It's Europa, one of Jupiter's 95 moons that likely has a vast liquid ocean hidden beneath its icy surface. The Europa Clipper spacecraft will travel all the way to this mysterious moon to answer one big question. Does Europa have suitable conditions to support life as we know it? Today, I'm joined by two incredible guests from NASA's Jet Propulsion Laboratory who are helping make this mission possible. First up, we have Cynthia Phillips, Europa Clipper Project Staff Scientist. Welcome, Cynthia.
Thanks, Tahira. I'm so excited to be here today.
And Jenny Kampmeyer, Europa Clipper Science Systems Engineer. It is great to see you, Jenny.
It's great to be here, Tahira. Thanks for having me.
Yeah, thank you both so much for being here. Can you start off by telling our viewers a little bit about your roles at NASA? Cynthia, we'll start with you.
Sure. Yeah. So I'm a project staff scientist on the Europa Clipper mission. And that means I basically work to help the project scientists and the science team make sure that the mission has everything it needs to be able to accomplish its top level science goals and objectives. And I'm also a planetary geologist. So I'm really excited about getting to see Europa.
And what about you, Ginny?
Yeah, so I'm the science systems engineer for Europa Clipper, and basically what that means is that I sit kind of right on the boundary between science and engineering. So I work really closely with the science team, helping to kind of explain engineering constraints and how they might affect the science that we're going to take. And then I also work really closely with the engineering team to make sure that we're getting, the most science, the best science we possibly can with this incredible spacecraft. So it's a really cool job getting to kind of, help work really closely with these kind of two sides of the project.
Yeah, and Ginny, we actually spent the day with you at NASA's Jet Propulsion Laboratory, where Europa Clipper was built, to learn more about your role in the mission as part of NASA's Behind the Spacecraft series. So let's take a look right now.
It's a surreal experience to know that we're doing some really humanity-changing science with the spacecraft. My name is...
So, those 50 flybys. So, those 50 flybys that we're going to be doing, that's going to give us kind of that global picture of Europa. We're going to be flying over lots of different parts of the surface and making sure that we can study this moon in its entirety.
Well, thank you both so much for that quick overview, but we already have so many questions pouring in online. It's actually pretty incredible. So let's jump right into this Q&A. And remember, if you're tuning in live right now, you can submit your own questions for Ginny and Cynthia using the hashtag AskNASA or by posting those questions into the comments wherever you're watching. So our first question is from Bruce on YouTube, who wants to know that since Europa is tidally locked to Jupiter, over time, wouldn't the oceans have shifted to the Jupiter-facing side of Europa instead of being uniformly spread around the moon? Cynthia?
That's a great question. So yes, so Europa is tidally locked. That means that one side of Europa always faces Jupiter and one side always faces away. And Europa orbits Jupiter about every 3.5 days approximately. So what we think, though, it's true that when Europa is closer to Jupiter, it gets tugged on, and that stretching and pulling produces tidal heating in the interior of the moon. And that's enough heating to keep this ocean liquid. So that's kind of the heat source that keeps this moon from just being frozen solid. It's this tidal heating, this tidal energy. But we think that the ocean is big enough, so it's global enough that heat is basically conducted, it's circulated through the ocean. So the ocean does stay as a whole global layer. It's not frozen on one side and liquid on the other side. Our evidence shows that it's actually a global frozen subsurface ocean layer, a liquid subsurface ocean layer.
That's great. And so we have a follow-up question from Brian on X, who wants to know, what specific data will the spacecraft be looking for at Europa? Jenny, you talked about that wonderful suite of instruments. Can you hit on this?
Data that we're going to be taking when we get there that's really going to help us understand this moon.
Cynthia, do you have any follow-up?
No, great answer. I'm putting you on the science team, Jenny.
Well, I have a great follow-up for you, Cynthia. So, Jenny just broke down all the data holistically of what we're really trying to look for in this mission. But we have Rocketman Randy on X who asks, what is the most promising indicator of life beneath the ice that you'll be searching for?
Yeah, so, we're not expecting there to be like multicellular, fish or anything in Europa's ocean. We're not going to complain if somehow, a fish gets thrown out and it, crashes into our spacecraft. We'll make sure we can see good pictures of it. But that's not what we're expecting to find here, right? So, most models of life on Europa, you're talking about like little tiny, like microscopic, single-celled kind of life forms. But even those would be super, super excited about. And so scientists have a lot of debates about what is a biosignature? What kind of measurement would you need to take to either detect life directly, or at least, tell you something about clues that maybe there's life. And so the dust detector and gas detector that Jenny was just mentioning are two of our best ways to make kind of as direct measurements as we can of Europa from orbit, so from space. And so like Jenny was saying, there's going to be particles that are thrown off of the surface of Europa, either through micrometeorite impacts, that's like little bits of space dust, crashes into the surface, and it throws up bits of Europa's surface into space. There's also charged particles from all that radiation. Those also hit the surface, and they could throw some of the surface off into space. And so basically, those particles make a really, really thin atmosphere surrounding Europa that we think is made of kind of little bits of the surface. And so on our close flybys, like Jenny was saying, we'll be able to use our dust detector and our gas detector to actually suck in some of those particles. So we'll actually take those particles on board the spacecraft into our detectors, and we can study their chemistry. And so, because those particles they've been ejected off the surface in a pretty high energy event, things like DNA, if it existed somehow on the surface, it would probably get really, really fractured. And so we're not going to be able to detect like big, huge, complex organic molecules. But what we will be able to detect is kind of the building blocks as these particles get broken down as they hit our detectors. We can measure kind of the fundamental chemistry that they're made of. And so that, in my opinion, is going to be one of our best kind of clues, one of our best signs that, maybe there's something really interesting going on there that could help lead us toward thinking that there could be life there.
And I know you mentioned earlier, just to have a building block by itself doesn't necessarily mean that there's habitability. They all need to be like in context of each other. And so could you talk more about the bigger picture of how these individual observations can tell that bigger story that Clipper's trying to find?
So the one of the really cool things about our instruments on Europa Clipper is that they're all designed to work together. So on some spacecraft previously, you had to fly by, and then if you wanted to take a picture with your camera, you have to rotate your spacecraft in one direction, and then to use the radar, you have to rotate it in a different direction. And so we made sure in Europa Clipper that all of our remote sensing instruments, all of those imagers that Jenny was talking about, they're all pointed in the same direction. So basically on each flyby during close approach, we don't have to pick. We can basically take observations of the same part of the surface with all of our instruments. And then at the same time, we're also collecting, the gas and the dust that are spewed off the surface. We're collecting those at the same time with our gas detector and our dust detector. We're taking those radar measurements, we're taking those gravity measurements, and those magnetic field measurements. So basically all of those are going to be taken simultaneously on each flyby. And so that's just really exciting because as a geologist, you get a lot of information from pictures. And I mean, I'm a pictures person. I love pictures of Europa, but being able to understand more about those pictures by having, the compositional information and then having the radar information to tell you the 3D structure and then having information about what was the magnetic field measurement right there as we flew by. It's really going to be the combination of all of these different instruments that's going to help us understand Europa. It's going to be fantastic.
Yeah, what an engineering marvel. Congratulations, Jenny, and to your team. And so we've been talking a little bit about images, and I know that's something that a lot of people are looking forward to. We have Antonio Gallo on X who asks, what will be the expected image resolution of the images that Clipper will provide? And what size of the objects on the surface will it be able to see? So essentially, like, how much is that surface visibility going to be for us? Jenny, I see you shaking your head. Do you want to do this one?
Yeah, I think I might actually toss it to Cynthia. I think I know the answer, but I think she'll know it for sure. So
yeah, so the highest resolution pictures we'll get will be at a resolution of about 0.5 meter per pixel. So that's about 1.5 feet. And so basically we'll be able to see things that are, like 3 feet across. And so, if there's a car driving around in Europa, we'll be able to see it really well. And yeah, I know, it's crazy. And we'll also be able to use those pictures to get stereo. So not only will we'll be able to see kind of car-sized objects on the surface, but we'll also be able to see, how tall they are, what their sort of 3D structure is. And that's just going to be amazing.
And so I have a follow-up question. Honestly, maybe both of you could answer it. So we have a viewer on YouTube who asks, what considerations went into selecting Europa for this mission over the other potential targets like Titan or Ganymede? Do we want to take it from science or engineering?
Yeah, well, I'll at least start by saying that I want to go to all of these places. So I think it's just a matter of, when we get to go, right? So we're going to Europa now, which is incredible, and there's so much we're going to learn there. It is, of course, kind of one of our most promising places in the solar system to look for a habitable environment. We have, other missions that are being planned to these other bodies. Of course, there's a lot of excitement about Enceladus, too, a moon of Saturn that is also kind of an icy ocean world. So, just from a totally selfish perspective, I want to go to all of these places. So let's go.
Yeah, I'm totally with you. Just, build me a couple more Europa Clippers, Jenny, and we'll send them everywhere.
That's right.
The reason why, and one of the reasons why Europa was chosen to be kind of the next flagship destination was that coming out of the Galileo mission. So that was a mission in the late 1990s that studied Jupiter, the Jupiter system and its moons, including Europa. That was really when we sort of started this whole revelation of the idea of an ocean world, the idea that an ocean could exist out in the outer solar system beyond the Earth. And that really it expanded our whole idea of the habitable zone. We used to think that, to be habitable, to be a place where life could live, you had to have liquid water stable at the surface. And so you get into this kind of Goldilocks story where in our solar system, Venus is too hot and Mars is cold and Earth is kind of just right. And so discovering that worlds like Europa could have oceans, or Europa is kind of like the type example. It's kind of like the OG ocean world. Out in the outer solar system, here's this ice layer at the top, but then there's this huge liquid water ocean. And so really, we've been working on planning this mission for 25 years now. We've been talking about it. And then finally, about 9 years ago, we got the new start, which is when you sort of get the rubber stamp from NASA headquarters to say, okay, this mission's real. Let's go ahead and figure out how to do it. So yeah, but the other locations too, NASA's also working on the Dragonfly mission, which is going to go and explore Titan. That's an octocopter that's actually going to fly around in Titan's thick atmosphere. So that's going to be amazing. And in the latest the National Academies of Science put out a decadal survey every 10 years. And so they ranked an Enceladus mission called the Enceladus Orbilander as kind of the next big sort of ocean world flagship mission as well. So yeah, we're really excited to see exploration of all of those places.
And we'd be remiss too to not mention the JUICE spacecraft. JUICE launched last year. This is the Jupiter Icy Moons Explorer mission, and it's going to get there kind of around the same time that Europa Clipper will. The spacecraft has about 6,000 pounds of propellant on board. That's about half of the total mass of the spacecraft. So it's a huge amount of fuel. If you're looking at a picture of our spacecraft, the kind of center, piece where everything is mounted, most of the interior of that is 2 giant propulsion tanks that are filled with propellant. So that 6,000 pounds of fuel, though, is mostly used to make attitude adjustments, so to change which way the spacecraft is pointed, but also to change our trajectory. And, as we kind of are flying around Jupiter, flying past Europa, we will use that propellant to, help change things and help make sure that Europa is staying right in line where it needs to be, right, on its path. The actual journey from Earth out to Jupiter, so much of that speed is actually gotten from the launch itself. So when we launch off the surface of the Earth, we get a huge boost from our Falcon Heavy rocket. That gets us going really, really fast. The Falcon Heavy is a massive rocket, so it gets us a lot of speed. And then we actually are going to pick up a little bit of a kick from doing a Mars gravity assist and an Earth gravity assist. So we'll pick up a little extra speed from doing flybys of those 2 planets. And then we get going just really, really fast all the way out to Jupiter. And this should hammer home just how far away Jupiter is, that even with all of that speed from the launch and the 2 gravity assists, it's still going to take us about 5.5 years to get out to the system. So we have to be patient. Of course, it'll be worth the wait, but it is quite a long trip out there.
And I have a great follow-up for you, Jenny, from Mikey Wasabi on YouTube. Considering how far away it is, how long will it take for the images to transmit back to Earth?
Yeah, that's a great question. Oh gosh, I'm going to get this wrong, but maybe Cynthia remembers our one-way light time. I believe it's about 45 minutes, so an hour and a half round trip. Is that right, Cynthia? Okay.
Yeah, about that.
So it takes about 45 minutes for light to go from Jupiter to the Earth and vice versa. So if we send an image from Jupiter, it'll take 45 minutes for it to get here. And then those images have to get processed on the ground, and certain things have to happen. But we do release kind of all of that data pretty quickly out to the public, kind of as soon as we can. So it takes a long time for light to travel just between, again, the two planets, which should give you a sense of just how far away Jupiter is.
Yeah. Wow. Thank you, Ginny. Our next question is from Titan on X, who asks, how will Europa Clipper detect potential chemical or biological activity in Europa's subsurface ocean? Do we want to take this on science?
Yeah, I can take that.
Okay.
Yeah. So that's a great question. So a couple different ways. One of the things you can use is that magnetometer that Jenny was talking about. And so we'll be able to get more information from those magnetic field measurements. But then another really cool measurement we'll be able to do is we can use our near-infrared mapping spectrometer. So this is an instrument called MISE, and basically it takes pictures of the surface, but rather than just in red, green, and blue, it uses multiple wavelengths in the near-infrared. And those wavelengths are really diagnostic to there's absorptions that are based on different chemicals on the surface. And so we know from some of our preliminary data that we got from the Galileo spacecraft that a lot of the dark stuff that you're seeing in these pictures here, there's kind of this dark iceberg-like terrain, and then there's the dark kind of streaks along the surface that we know now are cracks and ridges. And those geologic features they're associated with places where we see more of this kind of non-ice material. Most of the surface, like the stuff that looks blue in this picture, that's mostly pretty pure water ice. But all of kind of the reddish, brownish stuff, those are places where there's higher concentrations of these non-ice materials on the surface. And so we think from our initial observations from Galileo, 25 years ago now, that we're talking about highly hydrated things like magnesium sulfate or sulfuric acid, but we just don't know for sure. And so the measurements that we'll get from this compositional imager will be able to give us just much more detailed information about the chemical compounds on the surface. And we think because they're associated with certain kinds of geologic features, like these cracks and like these disrupted areas, that those are places where material from the ocean has actually come up through the ice layer onto the surface. And so that's another way that we can kind of use our clue of our surface observations to tell us something about the composition of that deep subsurface ocean.
And as you were giving this explanation, Cynthia, we had some really beautiful images of Europa popping up on the screen. Can you remind us, so you said we're getting, about 0.5 meter resolution? What is the difference between those images we are seeing, which already look pretty incredible, to what we can expect for Clipper?
Yeah, so we have one high-resolution picture of Europa that was taken from the Galileo spacecraft. The highest resolution picture was at 6 meters per pixel. But we only have one picture at that resolution, just one little tiny postage stamp on the surface. And so here you're seeing some kind of global scale images from various spacecraft. But really the best we could do with Galileo was that single 6 meter per pixel image. And with Europa Clipper, we'll get images over almost 90% of the surface at a resolution of about 100 meters per pixel. So that's going to be amazing. We're going to be able to see, house-sized objects, no problem on the surface with this. And then we'll get images over some portions of the surface, so less than 90% at this 0.5 meter per pixel. So that's 12 times better than the best high-resolution picture we saw from Galileo. So it's just going to be amazing.
I cannot wait.
It's amazing to think that we like these are real photos that were taken by real spacecraft, right? And when I look at that picture from Voyager and then compare it to Galileo, the Voyager picture, it's like, oh wow, cool. There's like this like dark region, and then you look at the Galileo ones, and it's like, oh, that was actually like 4 or 5 different types of terrain in that dark region, and it just kind of looked all the same. And then we get these higher resolution images, and then suddenly it just completely changes our understanding of what we're looking at. And so to think that Europa Clipper is then going to do that again, like an order of magnitude, better images, it's really, really cool.
I have another great follow-up question. We're on the photo stream today. So we have Squid on Twitch, who asks, who decides what pictures get released to the public, and what is the criteria on that?
That's a tricky question that has an easy answer, which is everything gets released to the public. This is a NASA-funded spacecraft. This is paid for by your tax dollars. So thank you, everyone, for funding Europa Clipper. And in return, we're going to give you pictures. So basically, all of the pictures that are taken after some very sort of initial processing, we're going to post them all up on a photo archive. We've done this for other missions, like with Cassini and like with the Mars missions. And so, pretty soon after they're taken, there's just going to be a stream of pictures. You can go there every day and, look at what the new images are. And then we'll do some so those are called raw images. So basically that's just, it comes off the spacecraft. We do a little bit initial processing to turn it from like digital bytes into an actual picture you can see, and then bloop, it'll go right up on the website. But then we're also going to do some more complicated images when we see something cool. And so that'll be, our pictures some of them are going to be like a bunch of little squares, but it's much more easy to understand what's going on if you stick those all together into an image mosaic, or if you put together the different individual color bands to make a color picture, or if you combine information from the camera with information from one of those compositional imagers. And so those kind of like combined science products, those are going to be done with the different instrument teams working together, and those will be released when we have something cool to show. So all the raw data will just be out there for people to see.
And so, in terms of this data collection, we've got another viewer on Twitch who wants to know, when can the public see your results? As we're doing these flybys, is it going to be instantaneous? Jenny, how about you take this one?
Yeah. Sure. So we talked a little bit about how the one-way light time is 45 minutes. So, even the minute the camera snaps a photo, we don't get to see it even for a little while until that data, comes down. And even then, we have to store it on board, and then the data gets downlinked a little bit later. So there is kind of some processing time. We don't quite get like, live video feed from Europa. Mm-hmm. And then there's processing on the ground. And so, but we do try to release stuff basically as quick as we can, as soon as we get the data and can send it out to the public. And then, of course, there's kind of the bigger question of like, when will we have results, right? We may have the raw data, but when do we actually have can we draw some scientific conclusions? Obviously, that's a little bit harder to determine. It depends on what the question is that we're asking, who's doing the research, and do we have all of the data needed to answer those questions. So that might take years and years as those kind of scientific papers come out over time.
So we know that the images are available to the public, but is the data available as well?
Yeah, so one of the requirements for any NASA mission is that all of the data gets put into something called the Planetary Data System. And that's a free archive of scientific data from all of the NASA missions. And so, a mission like Europa Clipper, there's basically a period of time where you downlink the data, and then each of the investigation teams gets some time to, make sure that the data, that they understand all of the processing, that they understand what the data is showing, that there aren't any, mistakes or weirdnesses in it. And then once the data has been validated by the teams, then it's archived into this planetary data system. So the pictures are special in that just the raw images from those will be put online. But all of the data from the other instruments, it will be put into the planetary data system. There's often a delay of about, 6 months to a year. I don't know, Jenny, if you remember the data archiving plan, exactly when, say, the first batch of data goes in.
Yeah, that's about right. It does take a little bit of time for all that kind of processing and validation to be done, but the planetary data system, something you can go Google and it will pop up. This is a thing that is publicly accessible, and all of our data will end up there.
Very cool. So Cynthia, I know you mentioned that you are a geologist, but I know that you are also an astrobiologist. And so I have a very good planetary protection question for you. It is from Mad Perma on Twitch, who asks, do you think there is a possibility that we bring along some microorganisms from Earth that could find a new home on Europa?
Yeah, that's a really important thing that NASA has to be very careful of. So, because we think Europa could be a place with life, the last thing we want to do is, kind of like destroy or infect that life in the process of trying to detect it. And so NASA has a planetary protection office, and their job is basically to protect, different places in the solar system, so moons and planets, from contamination from the Earth, and also the reverse contamination, where if we bring pieces of, say, Mars or the moon or another place back from there to the Earth, we also want to make sure that we don't contaminate Earth with any of those materials. In the case of Europa, we're not going to bring anything back, so we don't have to worry about that. But we do have to make sure that we sterilize the spacecraft. And so that's something we've had to be very, very careful about. Is we built the spacecraft in a clean room at JPL. And if you remember in the video, so here you can see, here's the spacecraft in one of our clean rooms, and you can see how everyone in there is wearing what we call a bunny suit. And these are suits that basically cover your whole body, and you're wearing gloves and a mask, and you're basically making sure that, you don't sneeze on the spacecraft, right? You don't get little bits of skin or hair or anything stuck on it. And then all of the instruments, you can see how they're wrapped up in this kind of protective shielding. And then people are just very, very careful. And then the folks here, one of the things they do is they actually, they swab the spacecraft as well. So once the spacecraft was built, we had contamination control engineers that went in, and they basically took samples of every part of the spacecraft that they could get, their little swabs on, and then they cultured those in a laboratory. And that was basically because, you can never have a spacecraft that's 100% sterile. And so they wanted to know for sure, what are the microorganisms that we're bringing along with us, so that if somehow we did most of the outer parts of the spacecraft, they're going to get, a nice high dose of radiation. And so if there's any little microbes that were hitching a ride on the outside, probably they'll have been baked off, before we get to Europa. So.
Oh, so cool. Thank you for explaining that. I mean, to see the inside of the clean room and just behind the scenes of everything that goes into doing a mission like this, it's almost like a movie, it's very cool to think about. And so I have another question, that hits on this topic of doing what has never been done. Is Even Vital on X wants to know, are there any technologies that are being used in the instruments of Europa Clipper to optimize the detection of these key molecules? Jenny?
Yeah, absolutely. So we have 2 instruments on the spacecraft that are kind of specifically designed to look for particles, gas, dust, and that's our mass specs instrument and our SUDA instrument. So that's our mass spectrometer and our dust detector. And these are some of the most advanced versions of these kinds of instruments that have ever been flown in space. They've, maybe had kind of predecessor instruments, older versions of the instruments that have flown on previous spacecraft. And so these are some of the most advanced forms of, a spectrometer and a dust detector that have ever been flown in space, and we're bringing them with us to Europa. So, the technology that flies in space is a little bit different than technology that we might have kind of in a laboratory. And that's because our spacecraft hardware needs to be radiation hardened. It needs to be able to survive kind of crazy thermal environments as we, fly out to Jupiter. And kind of the
follow-up for you, it is Benjamin on YouTube, who wants to know, will it be possible to orbit in the projected path of water geysers as an opportunity to get as close to a chance to study what's under the ice from above it? So, flying through these potential geysers and
Exactly. So there is some evidence that there may be plumes. We call them plumes, but yeah, geysers is also a good word. There is some evidence that we may have plumes on Europa. And so, of course, there's a lot of interest in like, could we fly right through one and, directly sample some of that water? It will be kind of hard to predict, where those plumes are going to be. And, maneuvering the spacecraft to fly right through one is a very challenging thing. And of course, our trajectory has been planned out kind of well in advance. But that is exactly, what the viewer asked, that if we were able to sample some of that water from a plume, that would be water that's coming from underneath the ice, right? So it's kind of a direct measurement of some of the water. I don't know, Cynthia, if you want to add anything to that.
Yeah, and so one of the cool things is that our mass spectrometer and our dust detector, like Jenny was mentioning, they're really, really sensitive. So even if there are no plumes erupting, we'll still be able to measure just those very few particles that get thrown off the surface through those micrometeorite and other impacts. But if there's a plume, we'll get 100 times or more sample. We'll get a huge amount of material, and so we'll be able to make even better measurements with those instruments. So yeah, being able to fly through a plume is kind of like a stretch goal, right? We don't have to do it, but if we could, it'd be really cool.
Amazing. Yeah. Yes. And so, Cynthia, we have James White on YouTube who asks, as we are saying water throughout this show, are we meaning that it's H2O or is it just a liquid?
Yeah, so we're actually talking about liquid water. The same H2O that we have here in Earth's oceans is the same water that's out in the outer solar system. So yeah, an ocean of liquid water, liquid H2O with some salt in it. And the salt could be things like this, magnesium sulfate, which is like Epsom salt. So, we have that here on Earth, or it could even be sodium chloride, which is the same, table salt that we have here on Earth as well. So yeah, these are familiar materials in a really unfamiliar location.
Which is just it's still mind-blowing to think that, one, this exists, and two, that we are on our way to study it. And I have a follow-up question. I'm not sure if it's a science question or engineering question, but we'll start with science. And Cynthia, toss it to Ginny if you think that'll be better. But we have Sammy Connor on YouTube who wants to know, how thick does the ice need to be to protect potential life against radiation from Jupiter's magnetic field?
So it turns out that ice is actually a pretty good protector. It's a pretty good insulator from radiation. But then you'd want to dig down below that, what we call the radiation processing depth. So you'd want to dig down into a kind of a fresher, more protected depth. But again, you don't have to dig that deep. And then you could get some of this fresh material that hasn't been as fried by radiation.
Yeah, and what's cool is, so we only have, you were saying that, ice is a really good protector, right, against radiation, and 10 centimeters or a foot down, well, the ice on Europa is miles thick, right? We are kind of, our best estimates is that we might have an average of maybe 10 to 15 miles of ice on the surface. Nice. So, yeah, which is, a really thick kind of protective layer. And so, we were talking earlier about how the radiation environment is kind of good to sterilize the spacecraft, right? If we brought any little microorganisms along with us, it's a good thing to kind of, keep our spacecraft clean. But that doesn't mean that life can't exist in that environment. That's what's amazing about Europa, is that underneath that ice, because it's such a good protective layer, there's a really good, potential for a habitable environment.
So we have just a minute left, but could you both briefly answer this question from Ian Carter on X, who wants to know what one finding would make this mission totally worthwhile for you? We'll start with you, Cynthia.
Finding a fish, finding some kind of macroscopic life form. That would totally make it worth it. But honestly, just getting that first super high resolution picture of Europa at, 12 times better than anything we've ever seen before, that's going to be kind of my, okay, we've made it. There's my picture. Anything else, but, and we're going to get hundreds of those pictures too, but it's going to be that first one where I'm just going to be so excited.
Yeah, and for me, I think it's, I keep talking about the water and how much that excites me. I think, we have a really good understanding that there should be water there. We like kind of all of our research and models point to that, but getting confirmation that yes, there is an ocean and kind of here's how much of it, when I think about other bodies in the solar system, the moon and Mars have kind of ice at in the polar regions, kind of frozen and water in certain places. Of course, Earth has an abundance of water, but the fact that there's another place in our solar system that in such a harsh environment, but that could have this liquid water ocean underneath the surface is just, again, every time I think about it, I get chills, and it's kind of mind-blowing. And so getting the data back that says, yes, there's water and here's how much, that's going to be the thing that will make it all worthwhile for me.
Well, unfortunately, that is all the time we had for today, but this has been such a great show. Cynthia and Jenny, thank you for taking so many questions from our viewers, and good luck on that launch.
Thank you so much. It's going to be amazing
Thank
next
you,
week.
Tahira.
Make sure you watch.
Yeah, it's going to be awesome.
Yes.
Thanks so much for having us today.
And thank you to everyone who joined us online. We had some really fantastic questions today, and we just love getting to engage with you live.
Good morning and welcome to the Johnson Space Center in Houston, Texas. I'm NASA's Sandra Jones, and we're bringing you live coverage from Mission Control Houston of the upcoming return-powered flyby, in which Orion will fly behind the moon and perform a burn utilizing the orbital maneuvering system to send it on a trajectory back towards Earth. This engine has been used numerous times throughout Orion's journey thus far, following Orion's launch atop the Space Launch System on November 26th. All spacecraft systems are performing well, now 20 days into the flight of Artemis 1. Today, we're in the White Flight Control Room, where Flight Director Judd Freeling is leading the team on console for today's flyby and burn. We do expect to lose signal of Orion as it travels behind the backside of the moon, as the moon will be blocking the direct sight to the Deep Space Network. We're tracking that loss of signal to begin at 10:41 a.m. Central this morning and will last 30 minutes. While in the loss of signal, the return-powered flyby burn will take place with the Orbital Maneuvering System engine at 10:43 a.m. Central. This will be the longest burn of the mission so far. The burn will be 3 minutes and 27 seconds long, about 1 minute longer than the outbound powered flyby, where Orion was placed in a trajectory to head out to deep space. That burn occurred successfully on November 21st, and the outbound powered flyby sent Orion close enough to the lunar surface to leverage the moon's gravitational force and swing the spacecraft once around the moon toward entry into distant retrograde orbit. Following this, Orion remained in the distant retrograde orbit for one long elliptical orbit around the moon, lasting about 6 days. We're now on the return journey of our trip, and this last big push will bring Orion on the trajectory to head towards home. You are looking at a view of the moon, a live view, as well as the Orion spacecraft. Right now, Orion is 5,680 miles away from the moon. Orion is traveling at 3,800 miles per hour, and Orion is over 230,000 miles away from planet Earth. At the closest approach this morning, Orion will be about 80 miles above the lunar surface. That closest approach will occur when we are behind the moon in that period of a loss of signal.
We're about 2 hours and 38 minutes away from today's return-powered flyby burn. Again, this burn will occur with the Orbital Maneuvering System Engine, or OMS engine. This engine has been used for a variety of burns so far on the mission. And you're looking at a view here on your screen of the Orion spacecraft. That large engine on the very bottom of the European Service Module is the Orbital Maneuvering System, or OMS engine. This main engine is a repurposed Space Shuttle Orbital Maneuvering System engine that has flown in space many times before. It actually flew on 19 Space Shuttle flights, beginning with STS-41G in October of 1984 and ending with STS-112 in October of 2002. Now, the OMS engine is not the only engine on board Orion. There's also 8 auxiliary engines, which you see a few of here. Those are also located on the bottom of the service module in 4 sets of 2. Each of these engines can provide about 100 pounds of thrust, and these engines provide steering and can pulse on and off during burns. Again, this is a live view from the Orion spacecraft. Orion is 5,500 miles away from the moon, but closing in. At closest approach later this morning, Orion will be just 80 miles above the lunar surface. Orion has had quite the journey, now 20 days into this 25-and-a-half-day mission. Notably, during this flight, Orion beat the longest distance ever traveled for a human-rated spacecraft meant to return home. At its furthest point from Earth, Orion was 268,563 miles from our home planet. The views you're looking at right now of the moon are being gathered with the SAW cameras, or solar array wing camera. The solar array wings are those X-shaped wings that stick out of the bottom of the Orion vehicle, and they are used to collect solar power and distribute to the vehicle. But on the very edge of these wings, are cameras. As you rotate the solar array wings, you are able to capture different views of not only the vehicle itself, but also of both the moon and, earlier on in the mission, the Earth. If you're just joining us this morning, we are bringing you live coverage of today's outbound powered flyby burn. This burn will bring Orion in a trajectory to head back home for a splashdown on Sunday, December 11th. We are anticipating that burn to begin at 10:43 a.m. Central Time. But while we look ahead to the return-powered flyby, let's take a look back at some of the highlights from this historic mission so far. First up, we have the Space Launch System launching from Pad 39B at the Kennedy Space Center in Florida with its sights set on the moon. SLS blasted off at 12:47 a.m. Central on November 16th. Here you see the 4 RS-25 engines lighting up the Florida sky. And this video shows SLS and Orion's climb to orbit from the perspective of a camera on the rocket. It was about an 8.5-minute climb to orbit. And following liftoff and that climb to orbit, the translunar injection burn took place for Artemis 1. The TLI maneuver took place as the upper part of the rocket, officially named the Interim Cryogenic Propulsion Stage, fired one RL-10 engine, producing 24,750 pounds of thrust to accelerate the vehicle to more than 22,600 miles per hour, a velocity fast enough to overcome the pull of Earth's gravity and propel Orion out of low Earth orbit to send the spacecraft to the moon. The TLI maneuver precisely targeted a point above the moon that will guide Orion close enough to be captured by the moon's gravity. And right after that TLI burn, the interim cryogenic propulsion stage separated from Orion, which you did just see a video of that on your screen there. Later that day, we received our very first imagery of Earth, as well as a maneuvering engine as well. This video shows Orion as it approaches the moon for this burn. And following that burn, Orion completed its closest approach to the lunar surface, where it was just about 80 miles above the lunar surface. And then Orion completed the distant retrograde orbit, which enabled Orion to head out into deep space. Now, this photo that you're looking at on your screen was taken while Orion was in that distant orbit. And this was the furthest point that Orion reached during its mission. Orion was 268,563 miles from our home planet when this photo was taken on November 28th for solar arrays. And just last week, the distant retrograde departure burn occurred, which placed Orion in a trajectory to exit distant retrograde orbit and head back toward the moon ahead of RPF today, which we are awaiting and looking forward to. And here's some video just prior to that burn. And you can see Earth there in the almost center of your screen, right behind the solar array. So as you can see, Orion has had an exciting journey so far, but still a few days left in this mission. At this time, Orion is 5,191 miles away from the lunar surface. And we're under 2 hours and 30 minutes away from today's return power flyby burn. Again, this burn is slated to begin at 10:43 a.m. Central, and will be a 3-minute 27-second burn. Again, you're looking at a live view of the moon as it continues to close, as Orion continues to close in. Now, 5,058 miles above the lunar surface. Orion is traveling at a velocity of 3,933 miles per hour and is 234,000 miles from planet Earth. Now, in this image of Earth right now, we actually are able to view several Apollo landing sites rather. Of course, we are a bit too far away to make out any distinct features, but you are looking at the landing sites for Apollo 15, 17, 11, 16, and 14. And you are looking at a graphic here that shows a little more clearly those landing sites and Orion's path as it flies around it. Again, Orion is about 5,000 miles away from the lunar surface, so we won't be able to make out any details. And at its closest approach, Orion will be 80 miles above the lunar surface, still a little too far to make out any of those details. As we continue to get these great views of the moon, we did mention that NASA Flight Director Rick LeBrode is leading the team here in Mission Control Houston inside the White Flight Control Room during today's burn. But let's take a quick look at this video, which discusses the various flight directors of Artemis in a little bit more detail.
Flight CTO and flight loop.
Ready, come for cooling status.
Conoco AOS, good for copy.
Flight controllers generally focus on systems, subsystems of the vehicle, and they're more in tune with the detailed workings of their particular system that they're responsible for. Flight directors, on the other hand, are more in tune with what is the integration between all of the subsystems. What are we all marching towards? What's our mission objective?
Prop flight has the RCS holding together with the regs.
Really, your training starts when you become a flight controller. You know, you learn a lot by osmosis, and you kind of get a sense of a little bit of the job, but once you become a flight director, The amount of learning you do is exponential.
You don't become an expert, but you have to understand them at a depth where you could have the good conversation, ask the right questions to the experts who are the flight controllers. You spend a lot of time studying and then training, getting in simulations and running through all the motions and practicing the real-time situation scenarios in the training environment.
I am the Ascent and Entry Flight Director for Artemis 1. I will take responsibility of the vehicle after it launches. I'll also be the entry flight director, so once we come back to Earth, I'll have a team that will monitor and control the vehicle once it splashes down, and we hand that over to Melissa Jones, who is the NASA Recovery Director.
Splashdown. Touchdown verify. Copy.
I'm the lead flight director for the mission, really responsible for the overall development of the mission. We work directly with the programs. They provide us the mission priorities, and we build a timeline that's going to accomplish those mission objectives. We're responsible for building our team, getting our team trained and certified. We have a training team that helps us, but we have the overall responsibility for putting together the team that's going to execute the mission.
Confirmation of translunar injection burn cutoff.
When you go to a place like the Moon or Mars, you really have to be explorers. It pushes the boundaries of civilization.
We are having to develop new technology that's going to have to sustain the astronauts for these very, very long trips. And it just makes sense to test that in going to the Moon, where you're in a similar environment, but you're much closer. And in the event of an emergency type scenario, we can bring them safely back home.
Station, this is Houston.
We've had a lot of experience now in low Earth orbit, over 50, 60 years of experience, and we've learned how to do that pretty well. We've learned what the effects of the body are in low Earth orbit, but there's still things that we need to practice, and we need to be able to understand how you sustain life further and further and further away from our planet.
It's just so different from everything you learn when you do low Earth orbit. And that's what's making it so much fun. I'm every bit as excited about this mission as I was the first day I walked in the doors of Mission Control.
Orion is now less than 5,000 miles away from the Moon, 4,833 miles away to be exact, traveling at a velocity of 3,966 miles per hour. We're 2 hours and 13 minutes away from today's burn. We're still targeting 10:43 a.m. Central for that burn. Everything continuing to proceed smoothly this morning as we anticipate the return-powered flyby burn in about 2 hours and 11 minutes. This burn will last for 3 minutes and 27 seconds and will change the velocity of the spacecraft by 960 feet per second. And this burn will also place Orion in a trajectory to head back home ahead of a splashdown in the Pacific Ocean on December 11th. The next major milestone here in Mission Control Houston is when Flight Director Judd Freeling will poll the team of flight controllers for a go, no-go for the burn. We anticipate that poll about an hour from now. We're just about an hour away from today's anticipated loss of signal. That LOS is slated to begin at 10:41 a.m. Central. We will not have signal with the Orion spacecraft during this time frame because the moon will be blocking any signal to the Deep Space Network. It's at this point that Orion will complete its closest approach to the lunar surface. That closest approach slated to be at 10:43 a.m. and just seconds later at 10:43 and 23 seconds a.m. Central will be today's return-powered flyby burn, which commits Orion to a journey back home. Orion is now 4,571 miles away from the moon, traveling at a velocity of 3,996 miles per hour. Everything continuing to look good this morning ahead of the return-powered flyby burn. That burn will take place 2 hours and 4 minutes from now and will last 3 minutes and 27 seconds long. The burn will take place with the Orbital Maneuvering System engine, or OMS engine, located on the bottom of the service module of the Orion spacecraft. This engine is capable of having burns that last less than 1 minute to more than 16 minutes in length. The OMS engine is the main engine on the European service module and provides the primary propulsion for Orion's major in-space maneuvers. The engine produces 6,000 pounds of thrust and is equipped to steer the spacecraft, and it can also be used in some abort cases to safely return Orion to Earth should that be required. The OMS engine is actually a repurposed Space Shuttle Orbital Maneuvering System engine that has flown in space before on 19 Space Shuttle flights, beginning with STS-41G in October 1984 and ending with STS-112 in October 2002. There are also 8 auxiliary engines on Orion. These are also located on the bottom of the service module and can provide trajectory correction. And there are 24 smaller engines grouped into 6 pods, which can provide attitude control as well. So in total, the service module has 33 engines. But today, for the return power flyby burn, we'll only be using one of those. Everything continuing to look good here in Mission Control as Orion closes in on the moon ahead of today's return-powered flyby burn. Before and during the Artemis 1 mission, we asked the public to share your moon-inspired creations with the hashtag NASA MoonSnap. We have received thousands of submissions, but here are just a few of them. This is a mural painted by Nikki Adams. You can clearly see the Space Launch System rocket as well as the Greek goddess Artemis, after which the Artemis missions are named. Artemis is the goddess of the moon and the hunt, and I think you can see her arrows and a deer included in the mural as well. Next up, we have a photo submitted by Jessa Rodriguez. The title is Ben and Sophia Plot Their Course. You can see the inclusion of Snoopy in his flight suit as well. Snoopy is our zero gravity indicator aboard the Orion spacecraft. And the Snoopy inside Orion right now is dressed very similarly to the Snoopy in this photo. What we see here is a 3D printed art piece from Terramoto. The artist entitled this piece Lunar Specimen 001 and used real data from the Lunar Reconnaissance Orbiter to create this. LRO data is also being used to determine where astronauts will land on the moon during the Artemis 3 mission. And the last image we have to show you today is from STEM educator Susie Bennett. She taught her 130 students about the Artemis 1 mission and even got them to fill out boarding passes. There are currently 3.4 million names of the public flying aboard the Orion spacecraft safely stowed on a flash drive. Thank you to everyone who shared your moon-inspired creations with us. If you're interested in participating, just use the hashtag NASAMoonSnap. We're continuing to get some great imagery of the lunar surface here as Orion is 4,227 miles away from the moon, traveling at a velocity of over 4,000 miles per hour. This imagery is coming from a camera on the Solar Array Wing, or SAW. We expect to continue to get imagery up until the point that Orion does go behind the moon and is in that loss of signal period that we've discussed. That will be a 30-minute loss of signal period beginning at 10:41 a.m. Central Time this morning. And just 2 minutes after the LOS begins, or that loss of signal period, we will have the return-powered flyby burn occur at 10:43 a.m. Central, lasting 3 minutes and 27 seconds, utilizing the Orbital Maneuvering System engine. This is Mission Control Houston. You're looking at a telemetry-driven animation of Orion as it travels at 4,000 miles per hour, closing in on the moon, now 4,131 miles away. Orion is 234,940 miles away from home. Orion launched on November 16th and is in the 20th day of its 25.5-day historic test flight mission. Orion is an uncrewed test flight, but is performing critical checkouts of its systems ahead of a crewed test flight as part of Artemis 2. It propelled Orion into that trajectory, and Orion remained in deep space for about 6 days and broke the distance record during that time frame for the farthest distance from Earth traveled by a human-rated spacecraft meant to return home. Orion, at its furthest point from Earth, was 268,563 miles away. Following that, Orion hung out in deep space for a little longer, and just a few days ago we had the DRD burn, or Distant Retrograde Departure burn. This burn put Orion on a trajectory to head back towards the moon ahead of today's return-powered flyby burn. Today's burn is critical to ensure that Orion is on the proper trajectory to return back to Earth safely. We are now 1 hour and 42 minutes and counting away from today's anticipated loss of signal as Orion flies behind the moon and performs the return-powered flyby burn, which will set us on a trajectory to return back to Earth and splash down in the Pacific Ocean on December 11th. But now, as you can imagine, this moment can certainly be a bit suspenseful as we await Orion to emerge from the backside of the moon and regain communication.
Or a burn during that time, and we have a predicted time when we should reacquire the signal, and so everybody is usually staring at that clock. As soon as the signal comes in-house, there's a sigh of relief, and we check to make sure that the burn executed correctly and that the spacecraft is in good health.
So again, we are anticipating that loss of signal to begin an hour and 41 minutes from now. Today's loss of signal will last 30 minutes in length, during which time Orion will complete its closest approach to the moon and just seconds later perform the return-powered flyby burn, which will last 3 minutes and 27 seconds and will change the velocity of the Orion spacecraft by 960 feet per second. Orion is now less than 4,000 miles away from the lunar surface, 3,780 miles to be exact. And Orion is traveling at 4,115 miles per hour. Everything's still continuing to look good here in Mission Control Houston as we anticipate the return power flyby burn occurring at 10:43 a.m. Central, an hour and 41 minutes from now. Today's return power flyby will send Orion close enough to the lunar surface to leverage the moon's gravitational force and swing the spacecraft into a trajectory to return back to Earth. During Orion's mission, it surpassed the furthest distance for a human-rated spacecraft meant to return home at over 268,000 miles from Earth at its furthest point. Prior to the distant retrograde departure burn, Orion was in deep space in a distant retrograde orbit. This orbit is called distant due to its high altitude from the moon. It's about 40,000 miles past the moon in its orbit. This orbit is 30,000 miles further than the previous record set during Apollo 13, and again is the furthest in space any spacecraft built for humans has ever flown. The orbit is also called retrograde because Orion traveled around the moon opposite the direction the moon travels around Earth. Distant retrograde orbit provides a highly stable orbit where little fuel is required to stay for an extended trip in deep space in order to put Orion's systems to the test in an environment far from Earth. The orbit that Orion completed in this mission is different from the orbit done during the Apollo program, in which the spacecraft orbited much closer to the lunar surface in a more circular fashion. It's important for us to learn about how a spacecraft functions in a deep space environment, because as part of the Artemis program, the Gateway program is building a small human-tended space station orbiting the moon that will provide extensive capabilities to support NASA's Artemis campaign. Gateway will be built with international and commercial partnerships and will support sustained exploration and research in deep space, and will include docking ports for a variety of visiting spacecraft, as well as space for crew to live and work, and onboard science investigations to study heliophysics, human health, and life sciences, among other areas. Gateway will be humanity's first space station in lunar orbit to support NASA's deep space exploration plans. But before we get to that point, we are testing out the Orion spacecraft as part of the Artemis 1 mission. Again, we're 20 days into a 25-and-a-half-day mission. And today's return-powered flyby is the next major milestone in Orion's 25-and-a-half-day mission. This burn will slingshot Orion around the moon and place it on a trajectory to splash down in the Pacific Ocean on December 11th. We're now 1 hour and 35 minutes away from today's return-powered flyby burn. Orion is currently traveling at 4,157 miles per hour and is 3,529 miles away from the moon. Just prior to today's return power flyby burn, Orion will complete its closest approach to the moon. At closest approach, Orion will be 79 miles above the lunar surface. This closest approach, as well as the burn, will occur in our anticipated loss of signal period. That loss of signal slated to begin an hour and 32 minutes from now and will last 30 minutes long. The reason we will not have signal with the Orion spacecraft is because the moon is blocking the connection to the Deep Space Network during that time period. Again, today's LOS will be a 30-minute long loss of signal, but we are anticipating to regain communications with the Orion spacecraft once it comes around to the other side of the moon and is able to regain communications with the Deep Space Network. At that point, flight controllers here in Mission Control Houston will be able to analyze today's 3-minute and 27-second return power flyby and make sure everything performed as expected. If you're just joining us this morning, we are bringing you live coverage of today's return power flyby of the Orion spacecraft, an uncrewed test flight as part of the Artemis program. Today is flight day 20 for Orion, and there are about 5.5 days left in this test flight mission. Leading up to this event, today, the return-powered flyby, there have been several other key milestones that Orion has reached, so let's take a look back at the past 20 days. First up, we have the Space Launch System launching from Pad 39B at the Kennedy Space Center in Florida with its sights set on the moon. SLS blasted off at 12:47 a.m. Central on November 16th. And here you see those 4 RS-25 engines lighting up the Florida sky. You can also see the orange core stage as well as one of the 2 solid rocket boosters in this view. On the very top of the vehicle is the launch abort system and, of course, the Orion spacecraft, which is now closing in on the moon ahead of today's return-powered flyby burn. Now, in this video, you have a launch from the perspective of a camera located on the Space Launch System rocket. This video shows SLS and Orion's climb to orbit. It was about an 8.5-minute climb to orbit. You can see the rocket soaring over the launch pad. Following liftoff and the climb to orbit, the translunar injection burn took place. The translunar injection maneuver took place as the upper part of the rocket, officially named the Interim Cryogenic Propulsion Stage, fired one RL-10 engine, producing 24,750 pounds of thrust to accelerate the vehicle to more than 22,600 miles per hour, which is a velocity fast enough to overcome the pull of Earth's gravity and propel Orion out of low Earth orbit to send the spacecraft to the moon. The translunar injection maneuver precisely targeted a point on the moon that helped guide Orion close enough to be captured by the moon's gravity. And right after the TLI burn, the interim cryogenic propulsion stage separated from the Orion spacecraft, which you did see in this video here. You see it floating away in the distance. Later that day, we received our first imagery of Earth, as well as completed the first checkout of the Orbital Maneuvering System, or OMS engine, which all went smoothly. Orion was officially on the way to the moon. And then several days later, on November 21st, Orion performed the outbound powered flyby, also with the orbital maneuvering engine, rather. The outbound powered flyby is the sister to the return powered flyby, which will occur today. The outbound powered flyby, as the name suggests, takes place on the outbound portion of the trip, whereas the return powered flyby takes place on the return journey, as Orion is anticipating its return home. In this video here, you can see the Orion spacecraft, as well as the Earth in the distance and the moon off to the left. This was just before Orion flew behind the moon as part of that outbound powered flyby. After this, Orion was placed in a deep space trajectory where it completed a distant retrograde orbit. During that time frame, Orion traveled the furthest distance than any human-rated spacecraft meant to return back to Earth had ever traveled. And in this photo here, you see Orion take a photo of planet Earth from over 268,000 miles away. And in this photo here, you can see Orion's solar rays split the difference between Earth and the moon on flight day 14 of the Artemis 1 mission. This imagery was captured by one of the cameras on the tip of one of the solar arrays, the spacecraft's 4 solar arrays. And just last week, on December 1st, the distant retrograde departure burn occurred, which placed Orion in a trajectory to exit the distant retrograde orbit and head back toward the moon ahead of the return-powered flyby, which we're looking forward today. In this view here, you can see the solar array flexing, as well as an Earth in the distance there, almost in the center of your screen. So it's been a busy journey for the Orion spacecraft. Again, we're on flight day 20 of a 25-and-a-half-day test flight mission. Orion is now 3,238 miles away from the lunar surface. And we are just 1 hour and 26 minutes away from today's outbound powered flyby burn, which will last 3 minutes and 27 seconds and place Orion in a trajectory to head back home. The next major milestone that we are tracking this morning here from Mission Control Houston will take place in about an hour from now, when NASA Flight Director Judd Freeling will pull the team inside Mission Control for a go, no-go for today's burn. We're continuing to bring you live imagery of the lunar surface from the Orion spacecraft as it continues to close in. Orion is currently 3,091 miles away from the moon, traveling at a velocity of 4,238 miles per hour. If you're just joining us this morning, we are 1 hour and 18 minutes away from today's outbound powered flyby burn. This burn will be 3 minutes and 27 seconds long and will propel Orion around the moon in anticipation of a splashdown off the coast of California on December 11th. Leading the team here in Mission Control Houston during today's burn is NASA Flight Director Judd Freeling. But Judd is not the only flight director here at the Johnson Space Center in Houston, Texas, that is working the Artemis mission. So let's take a look at a few of the other flight directors.
Flight CTO and flight loop.
Buddy comfort cooling status.
Flight Echo AOS, good for copy.
Flight controllers generally focus on systems, subsystems of the vehicle, and they're more in tune with the detailed workings of their particular system that they're responsible for. Flight directors, on the other hand, are more in tune with what is the integration between all of the subsystems. What are we all marching towards? What's our mission objective?
Prop flight has the RCS holding together with the regs.
Really, your training starts when you become a flight controller. You know, you learn a lot by osmosis, and you kind of get a sense of a little bit of the job, but once you become a flight director, the amount of learning you do is exponential.
You don't become an expert, but you have to understand them at a depth where you could have the good conversation, ask the right questions to the experts who are the flight controllers. You spend a lot of time studying and then training, getting in simulations and running through all the motions and practicing the real-time situation scenarios in the training environment.
I am the ascent and entry flight director for Artemis 1. I will take responsibility of the vehicle after it launches. I'll also be the entry flight director, so once we come back to Earth, I'll have a team that will monitor and control the vehicle once it splashes down, and we hand that over to Melissa Jones, who is the NASA recovery director.
Splashdown.
Touchdown verify.
Copy.
I'm the lead flight director for the mission, really responsible for the overall development of the mission. We work directly with the programs. They provide us the mission priorities, and we build a timeline that's going to accomplish those mission objectives. We're responsible for building our team, getting our team trained and certified. We have a training team that helps us, but we have the overall responsibility for putting together the team that's going to execute the mission.
Confirmation of translunar injection burn cutoff.
When you go to a place like the moon or Mars, you really have to be explorers. It pushes the boundaries of civilization.
We are having to develop new technology that's going to have to sustain the astronauts for these very, very long trips. And it just makes sense to test that and go into the moon where you're in a similar environment, but you're much closer in the event of an emergency type scenario, we can bring them safely back home.
Station, this is Houston.
We've had a lot of experience now in low Earth orbit, over 50, 60 years of experience, and we've learned how to do that pretty well. We've learned what the effects of the body are in low Earth orbit, but there's still things that we need to practice, and we need to be able to understand how you sustain life further and further and further away from our planet.
It's just so different from everything you learn when you do low Earth orbit. And that's what's making it so much fun. I'm every bit as excited about this mission as I was the first day I walked in the doors of Mission Control.
Orion continuing to close in on the moon, now 2,774 miles away, traveling at a velocity of 4,300 miles per hour. And you are looking at a view of the bottom of the European space You are looking at a view of the European service module, the very bottom of it there. And you are seeing the large engine there in the center of the European service module. That's the Orbital Maneuvering System engine, or OMS engine. That's the engine that will be utilized during today's return power flyby burn. This is the main engine on the European Service Module and is a repurposed Space Shuttle Orbital Maneuvering System engine that has flown in space 19 times before, all on Space Shuttle flights, beginning with STS-41G in October 1984 and ending with STS-112 in October 2002. We are now 1 hour and 13 minutes away from today's return-powered flyby burn. That burn will last 3 minutes and 27 seconds, and will change the velocity of the Orion spacecraft by 960 feet per second. You're also getting a great view of the 8 auxiliary engines on Orion. And again, Orion continues to close in on the moon, now only 2,680 miles away from the lunar surface. Following today's closest approach to the moon, Orion will be only 79.2 miles above the lunar surface. We're now 1 hour and 8 minutes away from today's return-powered flyby burn. Everything continuing to move smoothly here in Mission Control Houston. As a reminder, we will lose signal when Orion crosses behind the moon. That's because the moon will be blocking the signal to the Deep Space Network. We are anticipating that loss of signal 1 hour and 5 minutes from now. That will be a 30-minute loss of signal. During this loss of signal period is when Orion will complete the return-powered flyby burn, that 3-minute and 27-second burn that will send Orion on a trajectory to head back home ahead of a splashdown in the Pacific Ocean on December 11th. And if you are just joining us this morning, we are bringing you live coverage of today's return-powered flyby burn here in Mission Control Houston. That burn is 1 hour and 6 minutes away from now and will be a 3-minute, 27-second burn that will slingshot Orion around the moon in a trajectory to head back to Earth and a splashdown on December 11th. But we have been getting some beautiful views of the moon, and I have a very special guest with me this morning. This is Juliana Gross. She's the Deputy Apollo Curator, and she's going to point out some of these amazing features that we have been seeing on the lunar surface in some of the shots that we have been getting. So thank you so much for joining. I really appreciate you taking the time.
You're very welcome. I'm very excited to be here.
Yes, absolutely. So can you talk a little bit about some of the features that we are seeing on the lunar surface here?
Yeah, absolutely. So if you look on the moon right now to the left middle area of the moon there, the bright spot that you see there, that's Copernicus crater. The dark region that is sort of like right in front in the middle center of the moon right now, that's the Imbrium basin. And so these are impact features that we have on the moon. So when the moon formed throughout its history, over its 4.5 billion years, has been bombarded by meteorites and asteroids. And for the Imbrium, that's the darker round area that you can see there, what happened is there's a massive crater, and so we call these a basin, and melt from the interior of the moon came up through cracks and then filled that basin crater. And you can imagine that as a big lava lake, and then it cooled to form basalt. The same thing happens at the moment on Earth. Hawaii is erupting, and that brings up basalt from the interior of Earth. So these basalt samples, when we analyze them and we look at these, we can learn something about the interior of the moon. I see that we lost our actual live view, but in this beautiful view that we can see here, you can really nicely see Copernicus right in the center, and that's brighter because it excavates crustal material, which is white or bright compared to the mare, which are basalt, which is dark. Oh, there we are back. So Copernicus is now in the lower right corner of that image. That's a fairly young crater, and that's why it still appears fairly bright, because over time, when the sun interacts with lunar rocks, it darkens over time. So we call that space weathering. Yeah.
And so we are flying fairly close to some of the Apollo landing sites now. We're a little too high above. We're about 2,000 miles away from the moon still to make out any features. But can you talk about a little bit about what the Apollo program studied in those landing zones, and maybe touch on how Artemis is going to be different, because we're going to be landing in an entirely different spot, right?
Yeah, absolutely. Apollo wasn't so much about science. It was more about like, hey, we're actually going to the moon and we can do it, and like the technology to show that we can do it. Apollo 14 and 12 sort of landed near Copernicus, like south of where Copernicus crater is right now that I pointed out in that region. And so Apollo 14 landed there in 1971, right above the Framora region, which is kind of like south of Copernicus, and it's right at the edge of that big Imbrium basin that I talked about. They brought back a lot of rocks. They were interested in the rocks that were excavated from Imbrium. So there's a lot of impact melt, as we call them, or breccias. And every time a rock gets exposed to like heat and pressure and started to remelt in like an impact event like that, it resets the internal clock. So when rocks form, they record the condition from which they formed, including the age, like the time when they formed. But every time there's an impact event and it gets remelted, that internal clock resets. Now we can take these rocks and then measure the ages of them. And so every time the clock got reset, we now have the age of that impact event. And so we want to know when Imbrium formed, because it's such a big event that happened on the moon, that we can put everything else in relative age to each other. So that why that mission was important. Apollo 12 landed in the Oceanus Procellarum region, which is sort of to the lower left and then going up. It's kind of like where that shaded, like where you kind of stop seeing the moon, you know, the boundary of the shade and the sunlight lit area. The little bright spot that comes up on the, what is that, lower left third of the moon, that is Aristarchus crater. So that's a super bright crater in that Procellarum region, which we're now seeing more and more of. So that's sort of the area where Apollo 12 landed. That landing was to sort of show that we can do a pinpoint landing. So they landed 200 meters away from the Surveyor 3 lander, and they actually brought a piece from Surveyor 3 back to Earth to like really show. And that then paved the way for future missions to like really like, hey, we can do a pinpoint landing. So we can go to like a more difficult terrain where we can land, where it's more ruggedy. And so that's where we went there. And so now you can see even more of the Procellarum region. Most of that is dark gray, as you can see, and so these are the basalts, and that mission brought back a lot of these basaltic materials. And then we can look at the ages, and it turns out that those basalts were very different, and they were younger than the Apollo 11 mission, than the rocks that they brought back, the basalts that they brought back. Now, Artemis is going to be super exciting because we're going to a very different region. So if you look at the surface here, and you can see that's mostly dark gray, so it's mostly basalts. You can see in the upper part of the moon that's still bright. That's what we call the highland crust. So that's the very old crust. So when the moon formed, there was a giant impact between two protoplanets. It collided, created a lot of heat, everything melted. The center part formed and became Earth. And then the debris cloud that surrounded it coalesced and then became the moon. So once upon a time, the moon was covered in a global magma ocean. So it was fully molten, right? And if you have a global magma ocean, you start crystallizing things. So now when you crystallize stuff that is denser than the melt, that sinks, right? And if you crystallize things that are less dense than the melt, that starts to float, like ice is floating on water, right? And so now we have these crystals crystallizing these minerals, and they are less dense, so they float to the surface and they build the crust. These crystals are called plagioclase. They're white. And so your crust that then forms on the moon is white. And that's why the moon looks so bright when you look at this image or in the night sky, because that's the old crust of, you know, the oldest rocks we have, and they're white in color. And so that's why this is so bright. Now the near side, so the side that we see right now, we see these dark patches, which then are the younger basalts that came to the surface once you start impacting it, and you take stuff away, you made these big basins, and then the interior remelts, and that melt comes up to form to fill these craters. That's very special. So it turns out that this Procalarium region where Imbrium sits in, where Apollo 12 landed, where Apollo 14 landed, all these rocks that were brought back, they have a weird component that we call creep. And it's spelled K-R-E-E-P, and it stands for potassium, rare earth elements, and phosphor. That entire martyr regions that you can see here is also has iron in it, lots of iron and lots of titanium, but the rest of the moon doesn't really have that. And so geologically speaking, all the Apollo rocks are really, really cool because they're very special, right? So if I would give you 6 missions and you land them on Earth and you land them all in Yellowstone National Park, and you collect all your rocks, right? You get, geologically speaking, really interesting rocks, but they're not representative for the United States or the rest of the world, right? So same happens with Apollo. Really cool rocks, geologically speaking, very interesting, lots of basalts, right? They all have this weird creep component, so they're all creepy. But the rest of the moon is very different, so they're not representative. Now with Artemis, we're going to go to the South Polar region. So that region is more representative compared to Apollo. We don't really expect a lot of basalts there, so that's more like a highland region. The South Polar region also has the largest impact basin that we have on the moon, and also the oldest. So if we can bring back rocks from there, we can hopefully date that really, really old impact region, and then get a better idea of when things happened on the moon and establish a timeline. Now we also know that the polar regions are really, really cold. And so ices or volatiles and gases on the moon, they freeze out in the polar region. So when we go there and collect rocks, we can also bring back these frozen samples and then learn something about where the water is coming from, whether it's moon or, there was lots of asteroids and comets that impacted the moon. And then so we can also learn about something about the water that was delivered to the Earth-Moon system, which most likely also ended up on Earth. And so we can learn something about our own history and how the moon formed and evolved over time better than we can with Apollo. We're missing a lot of rocks and processes with Apollo, and hopefully we can fill these gaps with Artemis.
You are a wealth of knowledge. Thank you so much for sharing all of that information. Now, as we continue to get closer and closer to the lunar surface, of course, these features are going to become more and more clear. Orion is now 2,000 miles away from the moon, but at closest approach today, it will be just about 80 miles above the lunar surface. So before you go for the day, it looks like we are starting to get some better views of that area that you were discussing before. Is there any other items or areas that have come into view since we've been chit-chatting that you think would be helpful to point out?
Yeah, so we see Kepler crater, which is sort of to the left and lower left of Copernicus, what I just pointed out. So it's this like grayish area with a little dot in the center. And then if you go from there further to the left, right at where the moon's shades are, so there's still a little lower left, that really bright area, that's Aristarchus crater. And that's a really young crater, and it's really bright because it brought up material from that crust that I saw, and that's this white rock. It turns out we have orbital reflectance data. So when we look at the light, the sunlight that gets reflected off the surface, we can make assumptions about the chemistry in that region. And it turns out that that region is, geologically speaking, really, really complicated. So it brought back up old crustal material, but we also see some basaltic material. And in the central peak, we see material that is silicic, so it's really, really high in silica, and that usually means there's some kind of evolved rock. And when we say evolved, on Earth, that usually means like granites and stuff like that. We don't really mean it that way here, but it has more silica content in it. When I say central peak, so what happens when you have a big impact into the crust rebounds and brings a central part comes up. If you think about it, throwing a rock into water, right, it makes a splash, and then the water rebounds and brings a kind of like a central thing up and then plops back down. So if you would freeze that water, it would stand up in the center. So that happens on the moon or on Earth as well, where like the crust rebounds. And so the central peak is the area that is the deepest
We're now 50 minutes away from today's return-powered flyby burn. This burn will slingshot Orion around the lunar surface and put it in a trajectory ahead of a splashdown on December 11th back on Earth. This burn will be a 3-minute and 27-second long burn and will be the longest burn of the mission utilizing the Orbital Maneuvering System, or OMS engine. You are getting a view of the OMS engine on your screen. It's in the very top left, the largest engine on your screen. The next major milestone that we're tracking here in Mission Control Houston is the Go, No-Go poll. During this poll, NASA Flight Director Judd Freeling will go around the room and poll each of the flight console positions to ensure that all is looking good ahead of today's burn. Orion is now less than 2,000 miles away from the moon, 1,756 miles, moving at a velocity of 4,563 miles per hour. At this time, Orion is over 237,000 miles away from Earth. And if you're just joining us, Orion is now 1,550 miles away from the moon. We are anticipating today's return-powered flyby burn to begin 43 minutes from now. This burn will last 3 minutes and 27 seconds. During the time period that the burn takes place, Orion will be in a loss of signal period because it will be directly behind the moon, and the moon will be blocking the signal with the deep space network. Today's loss of signal will last for 30 minutes. After we come back around to the other side of the moon, we anticipate regaining communications with the Orion spacecraft, and that's when the team here in Mission Control will be able to analyze the return-powered flyby burn and make sure everything went as expected. This burn is critical as we look ahead to a return and splashdown of the Orion spacecraft on December 11th. Today's burn will put us in a trajectory to enable that splashdown. And on your screen right now, you are seeing some movement here. This is taking place as the solar array wings get into the right configuration ahead of today's burn. A great view of the Orbital Maneuvering System engine, or OMS engine, coming into view on the European Service Module. That's that large engine on the very bottom of the European Service Module, and is the engine that will be used during today's 3 minute and 27-second burn. Again, this will be the longest burn done by the OMS engine so far, but the OMS engine can actually fire for up to 16 minutes if necessary. You're also getting a view of the 8 auxiliary engines on Orion. These engines can fire for less than 1 minute, up to 45 minutes in length. And these engines are used more for trajectory corrections. Each engine provides about 100 pounds of thrust and can provide steering during burns by pulsing on and off. Orion continuing to get in the proper orientation ahead of today's burn. We are tracking that burn 38 minutes from now. And again, during that burn, we will lose signal with the Orion spacecraft. The loss of signal will be 36 minutes from now. You're looking at a view from our data-driven animation of the Orion spacecraft. As you can see, we're now 1,317 miles away from the moon, Orion moving at over 4,700 miles per hour. At this time, Orion is over 238,000 miles away from Earth. Everything continuing to move smoothly this morning as we anticipate the return powered flyby burn 36 minutes from now. We are hearing that the Orion spacecraft is now in the proper attitude ahead of today's burn. From this view, you can see that orbital maneuvering system engine on the left of your screen, that large engine on the European service module. That's the engine that will be utilized during today's burn. You also see two of the auxiliary engines, as well as two of the solar arrays. On the tip of the solar arrays, on the wings of the solar arrays, are the SAW, or solar array wing cameras. Those are the cameras which are capturing the imagery that you see right now on your screen. Orion continuing to close in on the moon, now 1,100 miles above the surface of the moon. During today's closest approach, Orion will be just 80 miles above the surface of the moon. Here in just a couple of minutes, we do expect NASA Flight Director Judd Freeling to give a go, no-go poll for today's return-powered flyby burn. If the team polls go, then we are anticipating the burn to begin at 10:43 a.m. Central and last 3 minutes and 27 seconds. This burn will slingshot us around the moon and get Orion into a trajectory to return back to Earth and splash down off the coast of California. While Orion is behind the moon today, we will not have communication with the vehicle because the moon will be blocking the connection to the Deep Space Network. However, once Orion swings back around on the other side of the moon and regains communications with the Deep Space Network, we do anticipate to be able to communicate with the vehicle. Today's loss of signal is slated to last 30 minutes. And at this time period, we are now 1 hour away from we are now 29 minutes away from the loss of signal and about an hour away from the acquisition of signal. If you're just joining us this morning, we are bringing you live coverage of today's return-powered flyby of the Orion spacecraft, which is now 20 days into its 25.5-day test flight. While this Orion spacecraft is uncrewed as part of Artemis 2, we will have crew on board Artemis 2. Today's return-powered flyby will begin at 10:43 a.m. Central and will last 3 minutes and 27 seconds. This burn will slingshot Orion around the backside of the moon and put it in a trajectory ahead of a splashdown off the coast of California just a few days from now on December 11th. During Orion's mission, it broke the record for longest distance traveled away from Earth for a human-rated spacecraft meant to return back to Earth. On November 28th, Orion broke that record, having traveled 268,563 miles away from our home planet. During this time period, Orion was in the distant retrograde orbit. Orion remained in this distant retrograde orbit for about 6 days, in which we tested out the systems of the spacecraft in the deep space environment. Last week, the distant retrograde departure burn took place, which brought Orion back towards the moon, which we are now less than 1,000 miles away from. The DRD burn set us up for today's return-powered flyby burn. And this burn again sets us up for splashdown just a few days from now. And here is the view of the moon, as mentioned, less than 1,000 miles away. Still a little ways to go to get to our closest approach of the day, at which point Orion will be just 80 miles above the lunar surface. But we are getting closer to today's anticipated burn, now 27 minutes away from that burn, and just 24 minutes away from the anticipated loss of signal. Orion continuing to pick up speed as it closes in on the lunar surface, now traveling at 4,852 miles per hour, and now just 846 miles away from the moon. We're continuing to get a shot of the Orion spacecraft, namely the European Service Module and the Orbital Maneuvering System, or OMS engine, on the left hand of your screen there, the largest engine shown. That's actually the largest engine on the Orion spacecraft. The OMS engine is a repurposed Space Shuttle Orbital Maneuvering System engine that has flown on 19 Space Shuttle flights. The first flight was STS-41G in October 1984, and the last was STS-112 in October 2002. And the go, no-go poll for the return-powered flyby is now underway. And the team here in Mission Control Houston did poll go for today's return-powered flyby burn. That burn will take place 23 minutes from now. And with the go from the team here in Mission Control Houston for the return powered flyby burn, we're now just counting down the minutes until the start of that burn. Again, 22 minutes away from today's burn. This burn will last 3 minutes and 27 seconds. But just prior to the burn, we will lose signal with the Orion spacecraft. That loss of signal is anticipated in 19 minutes from now. The reason we do lose communication with the spacecraft is because it will be flying directly behind the moon, and the moon is blocking the signal to the Deep Space Network. However, once the spacecraft travels back to the other side of the moon, we do expect to regain communications with the vehicle at that time. Orion is now only 687 miles away from the moon. At closest approach today, Orion will be just 80 miles above the lunar surface. Now just 20 minutes away from today's return-powered flyby. This burn will commit Orion to a trajectory to head back to planet Earth after its 20-day mission so far. By the time Orion splashes down in the Pacific Ocean, it will have been in space for 25.5 days. During its journey, Orion has broken the record for longest distance traveled by a human-rated spacecraft meant to return back to Earth. On November 28th, Orion was 268,563 miles away from planet Earth. Right now, Orion is 239,364 miles away from Earth, but only 570 miles away from the Moon. At our closest approach today, Orion will be just 80 miles above the surface. Our next set of events will take place in rapid succession. First, we will lose signal with the Orion spacecraft as it travels behind the moon. That loss of signal will be just 15 minutes from now. Then 3 minutes after we lose signal with Orion, the return-powered flyby burn, or RPF, will take place. This burn will last 3 minutes and 27 seconds and will be completed with the Orbital Maneuvering System, or OMS engine, which you see there on your screen to the left on the European service module. It's the largest engine on Orion. And today's 3 minute and 27 second burn will be the longest burn that the OMS engine will have completed on the mission so far. and we're continuing to get some great views of the lunar surface as we fly just 500 miles overhead. This view coming from one of the solar array wings or SAW cameras as it gets into the proper position for today's burn. Coincidentally, 8 years ago to the day was the launch of the Exploration Flight Test 1, or EFT-1. This was the first test flight of the crew module portion of the Orion multi-purpose crew vehicle. This was an uncrewed test flight that orbited the Earth 2 times before splashing down. Now, 8 years later, Orion is about to fly behind the moon. We're 15 minutes away from today's burn. We're now 13 minutes away from today's return-powered flyby burn. Orion is 365 miles above the lunar surface, traveling at a speed of 4,963 miles per hour. Just 10 minutes from now, we do anticipate losing signal with Orion as it begins its trip around the backside of the moon. On the bottom of your screen in the left there, you can see the solar array as it begins to move into place. You're also looking at the Orion capsule itself there, taking up the majority of your screen. You can see the kind of silver coloring of the capsule. This is the portion that when we have a crew on board as part of Artemis 2 that they will be living and working in during their trip to the moon and beyond. And in the top left of your screen there, you can see the moon as Orion glides over it, again 335 miles above the surface. But at the closest approach during today's return-powered flyby burn, Orion will be just 80 miles above the lunar surface. We are hearing that the solar arrays are configured for today's burn. Orion is now moving to the proper burn attitude. We're now 10 minutes and 30 seconds away from the start of today's 3-minute and 27-second burn. And we expect to lose signal with Orion in 8 minutes. Today's return-powered flyby burn sets us up on a trajectory to splash down off the coast of California just a few days from now on December 11th. And you were seeing some thruster firings there as Orion maneuvers to the proper attitude for today's burn. Now less than 6 minutes, 30 seconds until we lose signal with Orion. The burn will start in 8 minutes and 40 seconds. Orion is currently 253 miles above the lunar surface. Today's 3-minute and 27-second burn will take place with the Orbital Maneuvering System, or OMS engine. That's the largest engine on the European Service Module. Today's burn will change the velocity of the spacecraft by 960 feet per second during its 3-minute, 27-second burn. Closing in on 5 minutes away from our anticipated loss of signal with Orion. We will not have signal with Orion because the moon will be blocking out the signal to the Deep Space Network. However, when we swing back around on the other side of the moon, we do anticipate to regain those communications. And we are hearing that Orion is in the proper burn attitude. 6 minutes and 40 seconds away from the start of today's 3-minute 27-second burn. Just 4 minutes until today's loss of signal. As you can see from this telemetry-driven animation, Orion is now 202 miles away from the lunar surface. And you're looking at a live view inside the White Flight Control Room here at the Johnson Space Center in Houston, Texas. NASA Flight Director Judd Freeling is leading the team on console at this hour. We were tracking a loss of signal about 2 minutes and 40 seconds from now, but we are hearing that we did get that loss of signal a little earlier than expected, but that is to be anticipated from time to time. So now the next major milestone that we'll look ahead towards is the return-powered flyby burn less than 5 minutes from now. While we are traveling behind the moon, we do not have signal with the spacecraft because the moon is blocking the connection to the Deep Space Network. We anticipate that loss of signal to last about 30 minutes. And our counterparts here in this shot here in the European Space Agency Control Center in Noordwijk in the Netherlands. The European Space Agency's contribution to Artemis is, of course, the European Service Module, where the Orbital Maneuvering System, or OMS engine, is located. That's the engine that will be used for today's 3-minute and 27-second burn to propel us around the backside of the moon and commit us to a trajectory back to Earth ahead of a splashdown on December 11th. We're now less than 3 minutes away from the start of that 3-minute, 27-second burn. Right now, we do not have signal with the Orion spacecraft. That is expected as the vehicle is traveling behind the moon. This loss of signal will last about 30 minutes. And as Orion comes back around the other side of the moon, we will be able to regain communications with the vehicle. Now less than 2 minutes from today's return-powered flyby burn. And you do see the team here in Mission Control stand up and stretch their legs right now. Oftentimes they'll use this time to catch a quick break while the vehicle is in the loss of signal period. Again, today's loss of signal is expected to be about 30 minutes in length. One minute until the start of today's return-powered flyby burn. $30 until the start of today's 3-minute, 27-second long burn, committing Orion to a return home. $15 until burn start. And we do expect the burn to be underway. Again, this is a 3-minute, 27-second long burn. Because Orion is behind the moon and we do not have signal with the vehicle, we will not be able to confirm that the burn has began or the results of that burn until we come back around to the other side and regain communications on the Deep Space Network. Today's burn is being completed with the Orbital Maneuvering System, or OMS engine. That's the largest engine on the bottom of the European Service Module. Today's 3-minute and 27-second long burn will be the longest during the Artemis 1 mission used by the OMS engine, but the OMS engine can fire for up to 16 minutes in length. Now approaching the 2-minute mark into today's return-powered flyby burn, 1 minute and 27 seconds remaining. We're approaching the 3-minute mark into today's burn. Again, this burn is critical as it will slingshot us around the backside of the moon and place us on a trajectory ahead of a splashdown off the coast of California. 3 minutes into the burn, 27 seconds remaining. and we do expect the burn to be complete at this time. Again, because we are behind the moon and do not have signal with the spacecraft, we will not be able to confirm until Orion comes back around the other side of the moon. We are anticipating that acquisition of signal about 24 minutes and 45 seconds from now. And if you're just joining us, the return-powered flyby burn, the burn that is going to send Orion back around the other side of the moon in anticipation of a splashdown next week off the coast of California, has completed. Orion is still behind the moon at this hour, and we are in a period of a loss of signal. With the vehicle, we're anticipating to get that acquisition of signal back less than 24 minutes from now. But while Orion continues its journey around the moon, I do have a very special guest joining me today. This is Najud Moranci. She is the chief of the Exploration Mission Planning Office here at the Johnson Space Center in Houston, Texas. So thank you so much for joining us today, Najud.
Thank you. Glad to be here. Super special to be here for RPF.
Yeah, absolutely. It's an exciting moment indeed. This burn really commits Orion to a return journey home. But before we talk about that, I do want to talk a little bit about some of the work that your group is doing as part of the Artemis program. Now, this is an uncrewed test flight of the Orion spacecraft, but there's other components of Orion, including some robotics work that your group is working on. Can you talk a little bit about that and how it helps contribute to Artemis?
Yeah, there's a lot of different components to the Artemis as an enterprise, right? You know, Orion, SLS, this is our crewed vehicle to the moon, but we're also working on systems like Commercial Lunar Payload Service, which is delivering science payloads to the moon very soon, in the next year or so, hopefully starting those launches. And that's really the precursor for all of the logistics and the elements we're going to need as we build out a whole exploration enterprise on the surface of the moon.
That's great. I'm looking forward to seeing those land soon. And another aspect of your group is astromaterials. So during Apollo, many lunar samples were brought back to study, but during Artemis, we're going to be landing in a different location on the lunar South Pole. So how will our studies be different, and what will we be looking for this time around?
Yeah, part of our directorate includes the astromaterials and the curation of those materials. So all of the Apollo samples that came home came here to Johnson Space Center, and we have a dedicated facility that maintains them, manages the samples to send out to the science community for investigations. And that will also happen, they already do that for other samples, like the comet samples that come back from Hayabusa and Genesis. And as we bring Artemis samples home, they'll also be managing those and curating them. And really some of the advances in the science and measurements that we can make today that we did not have in Apollo are already getting prepared.
Great. And the very last thing I wanted to chat with you about today was the moment we've all been waiting for today, the return-powered flyby burn that occurred just 7 minutes and 9 seconds ago. So you had talked a little bit about this burn and why the timing of it was important on a Twitter post that you had shared. So can you talk a little bit more about that for the folks who maybe didn't see that?
Yeah, so all of the burns are very well calculated for specific reasons. So these burns have to be executed within moments of the timing, but really what it's doing is it's timing the return trip to Earth and then targeting so that when Orion travels behind the Earth, that's when the Pacific Ocean will be underneath the entry corridor. So we're targeting for a very thin slice of atmosphere, and that's where we do our aero capture. So the atmosphere actually slows Orion down, and we need to make sure all of that is set up precisely so that we can enter the atmosphere while the Pacific is where the entry targeting is, so that we can be landing right where the recovery forces are. So there's a lot of calculations that go into it by the wider trajectory team, but this is truly our deorbit burn. So we are doing a major maneuver right now which targets our entry in 6 days.
Great. Thank you for talking through that a little bit more. Again, that burn occurred 8 minutes ago, and once we acquire signal and we come back around on the other side, we'll be able to know if that burn was successful. We're looking ahead of that acquisition of signal now 20 minutes from now. But thank you so much, Najud, for taking some time. I know you're very busy, so I really appreciate you taking a few minutes to chat with us.
Thank you for having me. Like I said, it's really important what is going on, and I'm really excited to see this burn be successful for the conclusion of the mission.
Absolutely. We're now 17 minutes and 45 seconds away from the anticipated acquisition of signal following today's return-powered flyby burn, which took place about 11 minutes ago. That burn was 3 minutes and 27 seconds and committed us back to a return trajectory headed back to planet Earth, where Orion will complete its 25.5-day test flight mission around the moon and beyond. Now, the last time NASA made a journey around the moon in anticipation of a return home to Earth was during the final Apollo mission in 1972. That crew launched nearly 50 years ago to the day on December 7th, 1972. As part of that flight, Commander Gene Cernan and Lunar Module pilot Harrison Smith walked on the moon, while Command Module pilot Ronald Evans orbited above. The crew splashed down on December 19th, 1972, and completed 3 spacewalks during their mission. And during Apollo 17, they orbited the moon 75 times. Now less than 15 minutes until we expect to regain communication with the Orion spacecraft. If you're just joining us today, 13 minutes and 30 seconds ago, the orbital maneuvering system on board Orion fired for 3 minutes and 27 seconds, propelling the spacecraft around the moon and placing it into a trajectory ahead of a return back to Earth. Orion will splash down on December 11th, completing a 25-and-a-half-day uncrewed test flight in which it broke the longest distance from Earth by a human-rated spacecraft meant to return back to Earth. At its furthest point from Earth, Orion was 268,563 miles from our home planet. We're about 13 minutes away from our anticipated acquisition of signal. As Orion flies around the backside of the moon, let's take a look back at what has gotten us to this point so far. First up, we start with the Space Launch System launching from Pad 39B at the Kennedy Space Center in Florida with its sights set on the moon. SLS blasted off at 12:47 a.m. Central on November 16th. You see those 4 RS-25 engines lighting up the Space Coast. You can also see the core stage climb up, as well as one of the 2 solid rocket boosters in this view. And on top of the vehicle is the launch abort system, and of course the Orion spacecraft now behind the moon. This video shows SLS and Orion's climb to orbit from the perspective of a camera on the rocket. It was about an 8.5-minute climb into orbit. You can see the launch pad grow smaller and smaller as the Space Launch System propels Orion into orbit. Following liftoff and the climb to orbit, the translunar injection burn took place. The translunar injection maneuver took place as the upper part of the rocket, officially named the Interim Cryogenic Propulsion Stage, or ICPS, fired one RL-10 engine producing 24,750 pounds of thrust to accelerate the vehicle to more than 22,600 miles per hour, a velocity fast enough to overcome the pull of Earth's gravity and propel Orion out of low Earth orbit to send the spacecraft to the moon. The TLI maneuver precisely targeted a point on the moon that guided Orion close enough to be captured by the moon's gravity. Now, right after that TLI burn, the interim cryogenic propulsion stage separated from Orion, and you do see that here in the video as it drifts further away from the spacecraft. Later that day, we received our first imagery of Earth, as well as completed the first checkout of the Orbital Maneuvering System, or OMS engine. All went smoothly, and that Orbital Maneuvering System engine was used just 17 minutes ago for the return-powered flyby burn, which lasted 3 minutes and 27 seconds. Several days later, on November 21st, Orion performed the outbound-powered flyby burn, also with that orbital maneuvering engine. This is the sister to the return-powered flyby burn. The orbital maneuvering burn sets us up in a trajectory to head out to deep space. The return-powered flyby burn sets us up on a trajectory to return back home. This video shows Orion as it approached the moon for this burn. And as we mentioned in this broadcast several times, Orion has traveled further than any human-rated spacecraft, but in this view here that was taken just shortly before that, you can see an eclipse, the moon traveling in front of the Earth, a view we don't often see here on Earth. And this photo was taken on Flight Day 13, November 28th, when Orion reached its maximum distance from Earth, when it was 268,563 miles away from our home planet. Orion has traveled further than any spacecraft built for humans meant to return back home. And in this video here, you see Orion's solar rays split the difference between Earth and the Moon on flight day 14. This image is captured by a camera on the tip of one of the spacecraft's 4 solar arrays. And just last week, on December 1st, the distant retrograde departure burn occurred, which placed Orion in a trajectory to exit the distant retrograde orbit and head back toward the Moon ahead of today's return-powered flyby, which occurred just 19 minutes 15 seconds ago. In this view here, you can see the solar arrays, gimbal, as well as a Earth in the almost center of your screen there. So as you can see, Orion has had a busy journey in its 20 days of the mission so far, but it's not finished yet. We have about 5.5 days to go until splashdown. But today's return-powered flyby burn was the first step in getting us to the splashdown point. That burn commits us to returning home. We anticipate regaining communications with the Orion spacecraft about 8 minutes and 15 seconds from now. You're looking at a view inside Mission Control Houston. This is the white flight control room. The flight director during today's shift and return-powered flyby burn is NASA Flight Director Judd Freeling. You do see a few of the console positions looking a little empty. That is because we are in that loss of signal period. This is a great time for the flight controllers here in Houston to grab a quick break. Today's return-powered flyby burn occurred 22 minutes and 45 seconds ago. That burn utilized the Orbital Maneuvering System, or OMS engine, on board the Orion spacecraft. At this time, the Orion spacecraft is continuing to make its way behind the backside of the Moon, and we do not have signal with the vehicle. However, we do anticipate connecting with the vehicle now less than 5 minutes and 30 seconds from now. The reason we do not have communication with the vehicle is because when we are behind the Moon is blocking the signal to the Deep Space Network. We're now less than 4 minutes away from our anticipated acquisition of signal with the Orion spacecraft, which is currently traveling behind the moon following the return-powered flyby burn. This burn commits Orion to returning back to planet Earth. This return-powered flyby sends Orion close enough to the lunar surface to leverage the moon's gravitational force and swing the spacecraft into a trajectory to return back to Earth. Now, just before the burn began 25.5 minutes ago, Orion did complete its closest approach to the moon, at which point it was just under 80 miles away from the lunar surface. Beginning to see more folks trickle back into the white flight control room as we narrow in on our anticipated acquisition of signal with the Orion spacecraft, which is currently traveling behind the moon. Now 1 minute and 30 seconds away from our anticipated acquisition of signal with the Orion spacecraft. Once we acquire signal with the spacecraft, the team here in Mission Control Houston, namely the flight controllers, will be able to analyze the data that the vehicle is sending back to us in Mission Control. With that data, they'll be able to analyze if the burn was successful. Less than 1 minute away from our anticipated acquisition of signal with the Orion spacecraft. .30 seconds away from anticipated acquisition of signal. And we are standing by for acquisition of signal with the Orion spacecraft. And we do have confirmation of an acquisition of signal on the Deep Space Network in Goldstone at 11:12 a.m. Central. You're getting a view of the lunar surface from Orion's perspective. and we are hearing good confirmation that the burn was as expected. If you're just joining us, Orion completed its return-powered flyby burn, which slingshot it around the moon and committed Orion to a return trajectory back to planet Earth, hearing that that burn went smoothly and as expected. You are seeing a view on your screen of the lunar surface as well as Earth. For Orion, this is not a goodbye, but a see you later to the moon, our nearest celestial neighbor, as we begin to get our first glimpse of an Earthrise coming into frame. In this view, we see 8 billion human lives all existing upon our pale blue dot, our blue marble, our very own spaceship Earth. And after a long journey, Orion is now coming home. From this view, Orion is 1,277 miles above the lunar surface following its return-powered flyby burn, which sent it around the backside of the moon. Orion now has its sights set on home. Orion will splash down off the coast of California on December 11th. Wrapping up a 25-and-a-half-day mission. This is a view from inside the White Flight Control Room here in Mission Control, Houston. The team is being led by NASA Flight Director Judd Freeling. And this view from the Orion spacecraft as it looks to its target, planet Earth, flying over 1,200 miles above the lunar surface. At its closest approach following the return-powered flyby burn, Orion was just 80 miles above the lunar surface. The next time we see such a view, we will be hearing about it from a cruise perspective during Artemis II. Continuing to hear good performance following today's return-powered flyby burn. The Orion spacecraft is continuing to distance itself from the moon, now over 1,500 miles away from the lunar surface. Throughout the course of the next few days, we will see the distance from Earth continue to grow smaller and smaller. Orion is now 242,000 miles away from planet Earth. The spacecraft is moving at a velocity of 2,150 miles per hour. We're continuing to get some spectacular views from the Orion spacecraft. This view is from one of the solar array wing or SAW cameras on board the vehicle. The vehicle now over 1,680 miles away from the moon. And that small sliver towards the bottom of your screen, that's here, that's home, that's us. And that is where Orion is headed next. And with today's return-powered flyby burn now complete, and Orion having completed its closest approach to the moon at a distance of 80 miles above the surface, that will wrap up our coverage for today, but we'll continue to post daily updates about the mission on the Artemis blog at blogs.nasa.gov/Artemis, and we'll also be posting updates on our social media accounts. Later today, we'll have a briefing at 4 p.m. Central where representatives from NASA will discuss today's return-powered flyby, which we hope you'll tune in for. And we'll also be covering Orion's re-entry into Earth's atmosphere and its splashdown live on air next week. But until then, this is Mission Control Houston.
landing a man on the moon and returning him safely to the Earth.
Tranquility Base here. The Eagle has landed.
Feet, down at 2, feels good, 20 feet, going down at 2, 10 feet, 10 feet, contact, stop, push, engine stop, engine arm, proceed, command override off, mode control ahead, hold, pings auto. Okay, Houston, the Challenger has landed. Houston, you can tell America that Challenger is at Taurus Littrow.
"50 years ago today, Apollo 17 Commander Gene Cernan and Lunar Module pilot Jack Schmitt guided Challenger to a pinpoint landing on a barren rock-strewn area of the moon called Taurus Littrow. A half-century later, NASA's newest moon explorer, the Orion spacecraft, is barreling its way back home after circumnavigating the moon and beyond in an elliptical distant retrograde orbit, now less than 2 hours away from splashing down in the Pacific Ocean west of Baja, California, to complete its shakedown mission that has opened a new era of deep space exploration. Good morning from the Artemis Flight Control Room here at the Johnson Space Center in Houston and Mission Control, where the entry team of flight controllers is on duty, ready to bring Orion home to complete a 25-and-a-half-day mission. As he was for the launch of Orion more than 25 days ago, NASA Flight Director Judd Freeling is leading the entry team here in the White Flight Control Room. The target for Orion is growing larger in the field of view, moment by moment. This is a live view of the Earth from a distance of 15,000 miles away. About 3 hours and 40 minutes ago, Orion conducted the final major maneuver of its mission, a return trajectory correction burn of its thrusters to further fine-tune its path toward its splashdown site in the Pacific. We'll be heading out to the Pacific shortly for the first in a series of reports from the scene where Orion will be recovered. After launching atop the Space Launch System more than 25 days ago and traversing some 1.4 million miles in its circuitous orbit past the moon and back, the most critical phase of the Artemis 1 mission for Orion is at hand. It is homecoming day, so let's run down the milestones you'll be hearing about and seeing over the next couple of hours. Next up for Orion will be the crew module's separation from the European service module. That pyrotechnic separation is scheduled at 11 a.m. Central Time, just 20 minutes before Orion begins its entry into the Earth's atmosphere at an altitude of 3,200 statute miles. Now, we had planned for Orion to conduct a maneuver called the raise maneuver, a 16-second thruster firing to orient itself at the proper angle for its plunge back into the atmosphere. But the latest targeting for Orion from the flight dynamics folks here in Mission Control indicates such a precise trajectory for the spacecraft, it was determined that the raise maneuver was not required. That could still change following crew module, service module separation, but at the moment, the raise maneuver will not be required. The major objective of this mission is to test the spacecraft's heat shield against the searing heat of entry, where temperatures will build up to around 5,000 degrees Fahrenheit around Orion, half as hot as the outer surface of the Sun, twice as hot as the temperatures endured by returning space shuttles and other crew vehicles. Orion will perform what is called a skip entry. dipping into the atmosphere, then lifting out of the atmosphere and dipping back in like a flat rock skimming across a pond. This will provide aerobraking for the vehicle, will help to dissipate some of the vehicle's inertia, and will provide data needed in the future to select multiple splashdown sites for crewed missions. We are expecting 2 periods during entry when the buildup of heat-generated plasma around Orion will block communications and the receipt of data with flight controllers here in Houston. The first blackout should begin around 11:20 a.m. Central Time for just under 5 minutes, right around the time of peak heating on Orion, as it travels about 25 times the speed of sound. The second blackout period is expected around 11:29 a.m. Central Time for just under 3 minutes, right after the skip entry maneuver is complete. About 5 minutes after we regain communications with Orion, the pre-programmed commands stored on board will trigger the deployment of 3 parachutes at the top of Orion to pull the forward bay cover off of the crew module. That will initiate the sequential deployment of 2 drogue chutes and 3 pilot parachutes, followed by the 3 large main chutes to slow down Orion, enabling it to gently splash down in the Pacific. The current splashdown time, 11:39 and 42 seconds a.m. Central Time, 9:39 and 42 seconds a.m. Pacific Time. We'll be talking more about those parachutes shortly. The weather forecast at the splashdown site west of Baja California is excellent. The Spaceflight Meteorology Group here at the Johnson Space Center has just issued a forecast calling for scattered clouds at 1,700 feet, winds peaking to about 9 knots with periodic wave heights of about 5 feet. That is all within flight rule limits, and it should be a splendid day for Orion's homecoming. Out in the Pacific, aboard the prime recovery ship, the USS Portland, embedded with the Kennedy Space Center's Exploration Ground Systems Recovery Team and the U.S. Navy, is my colleague from the Kennedy Space Center, Daryl Nail. Daryl, good morning to you, and as they say in the Navy, give us a sit rep on preparations out there.
Well, good morning to you, Rob, and that's right. We're live on the deck just outside the bridge here on the USS Portland with a fantastic view of the area of splashdown. I just spoke with the recovery team. They say we are currently 5 miles away from the splashdown location right here in the Pacific Ocean. The location, as you mentioned, just off the coast of Baja, Mexico. We got the great weather report, seas, as you mentioned, 4 to 5 feet. We're looking good there. Let me show you the bridge deck where we are currently positioned. This is looking forward for the ship. I talked to Captain John Ryan, who says that he currently has the ship in a racetrack going around the location near where splashdown is, just upwind of it, so that the debris that comes down, that being the crew module and the parachutes, the forward bay cover, when it separates, will be all downwind of us. Now, preparations are already underway. We can hear the helicopter engines running, so we want to take you to a live view of the flight deck. This is towards the back of the ship, where just 5 minutes ago, the Navy started the engines on 2 of the 3 Navy MH-60s, or Nighthawk helicopters, that will be used for the operation. There you see them on your screen. The 2 helicopters on the left side of the flight deck, they will be involved in the operation. The third to the right is a backup helicopter. Now, one of the helicopters will use the Navy's infrared targeting system, which will start looking for Orion at an altitude of about 50,000 feet. Should be able to quickly lock on to Orion's heat shield, which should be still very hot after reaching 5,000 degrees Fahrenheit on the heat of reentry. The second helicopter will track the forward bay cover, a 1,000-pound, 9.5-foot wide titanium cover on top of Orion, which protects the parachutes during the heat of reentry. It is jettisoned to allow them to come out. Now, NASA's plan going in was to recover it, but they've made an adjustment due to the seas and the limitations of a small boat crane needed to lift it out of the water. Both helicopters, if you can see just to the left of that helicopter at the bottom of your screen, have GSS cameras mounted to them. These are ultra high def cameras to record 8K resolution video for engineering purposes. Now, with those helicopters just minutes away from flying out, let's take a look underneath this very flight deck. You can see into the well deck, and this is the multi-purpose capability of this vessel, the USS Portland. Down on the well deck is where the final phase of recovery will happen. 2 teams of Navy divers are preparing to launch the small boats. You see them at the bottom of your screen, just partially protruding there at the bottom. Those are inflatable boats that the Navy will use. 6 in all will pre-position themselves in the open sea to recover debris from the descent operation and then, of course, secure the Orion crew module itself. The Navy dive team will also take above water and underneath water photography of the heat shield before the crew module is moved. This is for all engineering purposes so they can see it freshly returned from space. Once the divers have Orion stabilized with tow ropes, you see that bright yellow structure right dead in the middle of your screen. That is the cradle that the boats and the winch lines will pull into position and put it right down on top of that cradle. They will flood that deck with water, roughly about 6 feet, and then with a careful choreography of winch line and lines being pulled and maintained by sailors, they'll put it in position for its ride back to San Diego. Now, coming up, we'll speak to one of the Navy divers who will be in the water helping. In fact, he's on deck standing by in just a few minutes. He's ready to go into the water. We'll get some words from him before he goes out on his assignment. Looking good on the ship right now. Rob, we'll send it back to you in Houston.
Thanks, Daryl. And again, a live view from Orion as it continues its pinpoint journey back towards its splashdown site, not far from where you are out on the Pacific. We will be going back to Daryl Nail on the USS Portland frequently during the course of today's coverage. Orion is wrapping up, as we said earlier, a mission that will have spanned 1.4 million miles, having flown further away from Earth than any human-rated spacecraft designed to return humans to Earth. And of course, the big test that's coming up, the ultimate test of its heat shield that will repel temperatures that will build up around the base of Orion to about 5,000 degrees Fahrenheit at peak heating as Orion barrels back into the Earth's atmosphere. It has been an incredibly successful mission for the Orion spacecraft. We'll be talking to a variety of people about all that, officials and managers and engineers throughout the course of our coverage today. But for the moment, let's take a visual and interactive look at this mission with NASA's Philip Hargrove, who will use the moon board to explain it all.
Yes, welcome to the moon board here at the Apollo Saturn V Center. It's been a super exciting month since the Artemis 1 launch. So let's take a look back at everything that happened just a few miles away from where I'm standing right now. Now, on November 16th at 1:47 a.m., the SLS lifted off from Launch Pad 39B here at Kennedy Space Center, and it put on an incredible show for everybody watching here from the Space Coast. I can't even describe to you how amazing it was to watch that core stage. Those solid rocket boosters provide over 8 million pounds of thrust at liftoff. Now, those boosters and the core stage got us going from 0 to over 17,000 miles per hour in just about 8 minutes. And then once all that propellant was depleted, the responsibility was passed on to the interim cryogenic propulsion stage. Now, the first job of the ICPS was to perform a perigee-raise maneuver, and this means that we're getting into a low Earth circular orbit that allows us to deploy those solar panels, start harvesting energy, and do systems checkouts to make sure that we are ready for our journey. And we stayed in that orbit for about 30 minutes, and then we did our translunar injection burn. This is the primary responsibility of the ICPS because it gives us the energy to escape low Earth orbit and commits us on a path out to the moon. Now, once it completed that burn, the ICPS separated from the Orion, and it performed one final burn to completely leave the Earth-Moon system. And after doing that, Orion was on its way out to the moon. So it spent about 4 days heading out towards the moon, and then we quickly dipped in about 60 miles above the surface of the moon and did an outbound powered flyby. Now, that powered flyby means that we're taking advantage of the speed we already have the gravity of the moon, and the energy we get from the service module's engines in order to target our orbit. And the orbit that we were targeting is called a DRO, or a distant retrograde orbit. And what that means is that instead of moving counterclockwise relative to the Earth like the moon does naturally, we are moving clockwise. So we're going in this opposite direction. That's what retrograde means. And distant means that we are going farther away than we have with any human spacecraft before. We're orbiting about 38,000 miles above the surface of the moon. And this is a really convenient orbit because we're able to stay there without having to use a ton of fuel for station keeping. And it also provides a safe, efficient path back home when we're ready. So this allowed us to learn how to operate in deep space, one of the core tenets of this mission. And then once we were ready, we started our trip back home. So we performed one more powered flyby, this time targeting our return, where we lit up those engines as we dipped close to the surface of the moon. And then we began our return transit, which took about 7 days, and that leads us to today. So next time we'll talk a bit more about what that return looks like and what our entry is actually going to look like. But until then, back to you.
Thank you, Philip. And again, a live view of Orion closing in on planet Earth, now about 11,000 miles away from Earth, as it continues a very, very precise trajectory for a splashdown that is scheduled at 11:39 and 42 seconds a.m. Central Time this morning. For Orion, launch from the Kennedy Space Center occurred on November 16th on the world's most powerful rocket, the Space Launch System. The first outbound powered flyby of the moon was performed 5 days later on November 21st, dipping to within about 81 miles of the lunar surface. That placed Orion on a very precise trajectory for its ultimate goal, that racetrack trajectory called the distant retrograde orbit, that would allow Orion the time and the space environment needed to test its mettle. 4 days later, Orion executed an engine firing to enter into that orbit, and the next day, Orion surpassed the record set during Apollo 13 52 years ago for the greatest distance ever traveled by a human-rated spacecraft designed to return humans to the Earth. On November 28th, Orion reached its farthest distance from the Earth, some 268,000 miles, before departing the distant retrograde orbit on December 1st. And this past Monday, Orion conducted a 3-minute, 27-second engine firing behind the moon to whip around Earth's closest neighbor for the final leg of its flight, passing to within 80 miles of the surface, turning for home, and its splashdown that is scheduled just 1 hour, 21 minutes, 44 seconds from now. The initial mission of the Artemis 1 program was always designed to be a test flight, wringing out all of the systems of the Space Launch System and the Orion spacecraft, and for more than 25 days it did just that, setting the stage for a crew to board an Orion vehicle for a trip around the moon in 2 years. So with that, out in the Pacific, where Orion will be splashing down not long from now, we're going to go back here in a moment to Daryl Nail, who's standing by with one of the first persons that will actually be in the water to execute the recovery and the securing of the Orion spacecraft. Daryl?
That's right, Rob, and his name is Wayne Shearer, and he is the Navy diver first class aboard boat number 2. He is the lead on one of the 2 small boats called Cricks, which are essentially small inflatable Navy boats. He's just about 20 or so minutes away from getting into that boat. Thank you, Wayne, for coming up here and making some time for us to tell us about the operation today.
Of course, sir.
So tell me exactly how your team goes about securing this spacecraft after it comes back from space, splashes down the water just a few miles from us.
Well, sequence of events are going to go splash down, wait 2 hours. We're going to do a hazard analysis, make sure there's no gas coming off of it. We're going to come up, take those pictures like you said earlier for those engineering purposes. Once that's done, then we put the what's called a pony collar on it, and then basically it's a sequence of events of pulling all those ropes out like you said earlier and pulling it into the well deck. Easy day.
Easy day, and we know that there are certainly going to be some challenges, right? Seas are 4 to 5 foot currently, which is within your limit. Let's take a look now underneath the well deck to the boats that are currently being prepared. You're really literally going to be going down here and right to that boat after we conclude our interview. How will you manage the 4 to 5 foot seas with a bobbing spacecraft and bobbing inflatable boat with your team?
Well, this is just another day in the park for us. You know, we've trained for the last year and a half for this. We've been in worse seas than this, recovering anything under the water. It's just different. Instead of recovering something from under the water, we're going to recover something that fell from the sky.
You can see on our screen, those are the tip edges of your 2 inflatable boats. I imagine you'll be positioned somewhere towards the front or back?
I'll be positioned toward the middle of the boat.
Towards the middle of the boat. And as you do this operation, have you thought about just the importance of it? Reflecting that it is you who will be one of the first people to put your hands on a spacecraft that just came back from space.
I mean, definitely, this is probably every kid's little dream, or every little kid's dream, to be able to do exactly what I'm doing today, you know, and I think I can speak for the whole dive team that we're honored to be part of history and to be part of something so monumentous, and just ready and excited to go out and do this.
On a personal note, you and I were talking about how you got into the Navy and the dive team. What was it that motivated you to become a Navy diver, and then ultimately, now that you're on this operation, looking back at that choice?
Well, February 2003 from Leesville, Louisiana, and I heard a loud boom outside my window one morning, and I ran outside and talked to my dad, and a few hours later watching the news, and unfortunately what we heard was the USS Columbia break up. So, you know, it was not a great thing to hear, but it kind of jump-started my career of like, hey, what do I want to do? And I wanted to be out there to help people, and the Navy just kind of fell into my lap, and, you know, 20 years later to be able to be part of history of the next thing we've flown in space like that is absolutely a dream come true for myself.
Certainly a tragedy for NASA, one that has created many lessons learned for our agency, but interesting that it led you into this.
Around the world.
And briefly, Wayne, as you look out here to the Pacific Ocean, where you will literally be in the water in just a few minutes, will you be sharing any words with your team?
Good luck, be safe, and let's be part of history.
All right, we wish you the best. Wayne, thank you for taking the time, and good luck out there.
Thanks, sir.
Rob, we'll send it back to you.
Thanks, Daryl. It looks like a great day out in the Pacific, west of Baja, California, where Orion is headed. And you can't beat this view, though. The view of the Earth, where Orion is headed, tried and true, on a pinpoint course for a splashdown just 1 hour and 16 minutes from now. After Orion enters the Earth's atmosphere at the conclusion of this 25-and-a-half-day mission, the spacecraft is going to rely on a very heavily tested parachute system to slow down its speed and allow for a very gentle splashdown. Koki Machin, the chief engineer of Orion's parachute assembly system, now describes the process and the path to the certification of the parachute system. A series of 11 parachutes will be deployed in sequential fashion, a very dramatic return to Earth lying ahead for the Orion spacecraft.
Our design is almost exactly the Apollo design. The shape of the mains, the shape of the drogues. The only major difference is we are bigger. Apollo weighed roughly 13,500 pounds, and we weigh 22 and change thousand pounds. And so our parachutes are larger because we have more energy to take out of the system, and our parachutes are stronger. So at a fundamental level, all-round parachutes are alike. The Orion system has drogue parachutes that initially decelerate the system, and because they're deployed at a much higher velocity, they're made of ribbons. The ribbons can take the fluttering associated with high-velocity deployments much better than a solid canopy can. And once the system slows down, it deploys the mains. The mains are much closer to a personnel chute. They're called ring sails. The major difference would be that a personnel chute could be 28 to 30 feet in diameter, and a CPAS main is 116 feet in diameter. So the Orion parachutes are what we refer to as hybrid parachutes. The drag surfaces are nylon, but then the structural grid, how we take the drag on that nylon surface and transmit it down to the vehicle, is made of Kevlar. And Kevlar is quite a bit stronger and stiffer, and it just completely different material than the drag surfaces are. So the CPAS system is designed to safely recover the crew with just 2 mains deployed. The problem with deploying the backup chute after you deploy the first 2 chutes is you have to negotiate the chute that's already out there. So what we chose to do, and what Apollo chose to do, was to deploy the backup chute with the main system itself. And as a result, we get a much softer landing when all the parachutes work properly. But both systems were designed to land with just 2 main parachutes functioning. When we did the pad abort test at White Sands, I was quite scared. But I wasn't scared for our system. I was scared for the repositioning after the rockets took off the capsule and repositioned it. It was perfect. That thing reoriented like it was on rails. And I swear to you, this huge relief came over me when the cover came off, because I thought, wow, we're not done, but we're done. I know this system's going to work.
And there again, the view of the Earth. We're about 33 minutes away from the first big milestone. That will be the separation of the crew module and the service module, signaling the beginning of Orion's entrance into the home stretch of its 1.4 million mile journey. With us at this hour is the Deputy Associate Administrator for Exploration Systems, Kathy Kerner. Kathy, thanks for joining us this morning. It's great to see you.
Glad to be here.
You know, this is a little bit of deja vu for you. You were a flight director in this room for a number of years. Your thoughts as Orion approaches the end of this maiden flight?
Yeah, certainly a lot of history in human spaceflight has been made in this room, and we're making some more today. I'm really excited. There's a lot of energy in the room, and it's very familiar, but it's also very different as we step into this next episode in human exploration.
You know, the mission had its trials and tribulations getting off the ground, but once it did, so far, so good. The mission has exceeded expectations in many areas. Of course, the post-flight analysis is yet to come, but from the top level, the 1,000-foot level, looking down at the mission, what are your thoughts about what has been accomplished in setting the stage for a crewed mission 2 years from now?
Absolutely, this has been a phenomenal mission thus far. If you asked me to grade it, I'd give us an A+. I think that the work that has been performed both by the Exploration Ground Systems team, the SLS team, and the Orion team has been fantastic. We've been learning how the spacecraft operates. We've been learning how to fly this amazing machine,
and it's gone so well that we've actually been able to add tests during the mission that help expand the envelope that we're going to be able to use to operate the spacecraft once we have crew on board.
The major objective of the mission lies ahead. That's the rigorous testing of the heat shield, as we've just seen in our features. 5,000 degrees Fahrenheit building up around the spacecraft, twice as much as space shuttles endured when they re-entered the Earth's atmosphere. How do you think it's all going to fare, and what then needs to be done to analyze the performance of the heat shield in certifying that we are good to put a crew on board in a couple of years?
So this test, this is the primary objective of this test mission, but we've got a lot more objectives that we need to accomplish between now and when we launch crew. We have an environmental test that we need to conduct of the entire integrated spacecraft once we get the environmental and life support systems on board. So this is just one of many tests that we have going forward and one of many analyses that we need to do with all of the post-flight data that we retrieve from the spacecraft.
We opened up the broadcast paying homage to Apollo 17 landing on the moon 50 years ago today. It's only coincidence that this happened, but it seems very appropriate, doesn't it?
It does. It seems fitting that we would honor Apollo with the new legacy of the Artemis generation and this mission today.
Thanks very much, Kathy. Kathy Kerner, the Deputy Associate Administrator for Exploration Systems, and We're nearing the end of the home stretch here of this very first mission.
Thanks, Rob. Great to be here.
And as the Earth grows larger and larger in the field of view, Orion continues its trek back home with crew module, service module separation just 30 minutes from now. Entry interface just 20 minutes after that. In the meantime, let's go back out to the Pacific, the destination for Orion today, where Darrell Nail from the Kennedy Space Center, again embedded with the Exploration Ground Systems and Recovery teams, is standing by with Shannon Walker, NASA astronaut.
Well operations. All hands on the ball, staying clear of wing walls, bigger storage areas.
That's right, Rob. Shannon Walker, NASA astronaut, has been on board since we departed on Wednesday to come out to the site. Thank you for being here to take some time to talk to us amidst this important operation to recover the Orion crew module.
Absolutely. I am happy to be here.
So tell me a little bit about the reason you're here and what you're doing as you observe the operations today.
Yeah, of course, we do not have crew on this capsule, but I am here because the next Artemis flight will have crew on it. And so we are starting the process of assessing how we're going to operate with crew. How do we extract the crew from the capsule? How do we get them to the ship safely? How do we do all the medical checks we want to do? So we're starting the process of getting ready for the next Artemis mission.
And with this capsule being recovered today, it will be brought back. I imagine that the astronauts will be very interested in the data that comes off of it. This particular capsule has sensors all over it, more than any future capsule will have.
Yeah, absolutely. So this is going to tell us what we need to do, change, modify for the next Artemis mission.
On all flight quarter stations. The ship expects to read manned flight quarters at 0945.
And what you're hearing are some announcements from the ship PA informing the crew at what stage in the operation we're at. I should mention that we just had helicopters, the MH-60s at the back of the flight deck just launched off and are in flight now to the recovery area. They play an important role here. Shannon, continuing now with our interview, when you look at the operation as a whole, they're currently trying to determine how the astronauts will be recovered. That's not happening today.
That's right.
But that will have to be integrated into the operation. Do they come off immediately after the crew splashes down? Or there's an idea kicking around there to have them stay in the capsule and come to the back of the ship. What are your thoughts on both of those? What are the pluses and minuses on those?
Well, certainly the plus of having the crew come off immediately is that the crew is not staying in the capsule for an extended period of time. There'll be a time when we'll have to turn off the cooling in the capsule, which would mean the crew will start getting very warm in their suits. So it's better to get them off before that. Also, you'll probably see later the operations in the well deck. There are a lot of waves in there, and it's probably not going to be a fun ride for the crew to be in there. So you're right, we're looking at it. The actual, let's see, next summer, we're going to have another test run. We'll be out on a ship, and we will be looking at all the different methodologies for getting crew off the capsule.
And may I ask what your particular favorite would be? I mean, I think you've already kind of indicated you're leaning more towards let's get off the ship.
Off immediately. Yeah, so I think we will probably, now don't quote me on this, but we'll probably extract the crew via helicopter from the capsule and helicopter them over to the ship.
And as an astronaut, just briefly, when you come back from space, physically, you're in a condition where how would you describe it, physically and mentally?
Yeah, so when we come back, we consider crew deconditioned. While on the space station, for example, we have lots of exercise, so we're really strong when we come back. It is still a big adjustment to being in Earth's gravity again. The lunar missions is kind of in the middle between what we did in the shuttle days and what we're doing on the space station. So we don't know exactly how the crew's going to feel, but they're going to be exhausted, and so their balance may be off a little bit. So it's better just to get them out of the capsule. As far as the mental side goes, I found that when I am back on Earth, it's just a huge sigh of relief in that somebody else is worrying all the details, and I can just sit and relax a little bit.
Well, we appreciate you being here. Thank you for all the insight. You're doing a great job of staying balanced amidst the 4 to 5 foot seas as you see the horizon going up and down, right?
It is definitely a challenge.
Thank you very much, Shannon. Rob, we'll send it back to you in Houston.
Thanks, Darrell. Thank you, Shannon, and happy sailing out there as we continue to watch this scintillating view of the Earth. as we are just 1 hour, 5 minutes away from splashdown. Now, as Shannon Walker alluded to in that interview with Daryl Nail on the USS Portland, we're going to be on the air here for a couple of hours after splashdown, while a number of flight objectives and test objectives are being conducted, data gathering on the Orion spacecraft. But the whole recovery issue to get Orion into the well deck of the USS Portland is no small feat. Melissa Jones, who is the landing director and the recovery director from the Kennedy Space Center, has worked tirelessly to choreograph all of the elements of that recovery operation. Let's take a look now at how Orion will be recovered.
Today we are aboard the USS John P. Murtha, and behind me is a mock-up capsule of the Orion crew module, and we are training the team to be ready to do Artemis 1 recovery operations. My role as the NASA Recovery Director is to lead the interagency team that will recover the capsule. Ever since the Apollo program, NASA and the Navy have worked together to recover NASA's capsules in the water. So one of the huge benefits of working with the Navy is the fact that they're operational and we leverage their core competencies to bring the flight hardware and the crew back safely from the moon. On the Artemis 1 recovery day, my job will be to direct the team through the integrated operation to recover the capsule. The ship will get to the recovery location 24 hours before, and we will start launching weather balloons. And that data will go back to Houston and will help inform where we splash down. A couple hours before splashdown, the Navy launches small boats off of the knuckle boom crane, and helicopters will take off and they will do their circles in the air, and they are waiting for the capsule to re-enter so that they can get good data and photo imagery of the capsule on its way back to Earth. Once that is done and we splash down, we will safe the capsule, approach the capsule, attach lines to the capsule, and recover it into the well deck of the ship. Artemis 1 recovery operations will take about 5 hours to perform all of the work we need to do because we are gathering data so that we can fly crewed mission on Artemis 2. When Artemis 1 splashes down, it's going to be the culmination of all of the hard work that we've put in as a team. It's going to be an amazing feeling, hearing that we've met Earth's interface and that we can see 3 good main parachutes. And when we hear splashdown, I'm going to get goosebumps all over me.
And again, that whole recovery operation will take several hours. We are going to remain on the air for at least 2 hours or so after splashdown so that we can bring you all the information regarding the initial safing of the vehicle and the test objectives that the flight control team here in Houston, led by Flight Director Judd Freeling, will be absorbing all of that data, mostly about the thermal conditions of the spacecraft, which will have come through some 5,000 degrees Fahrenheit in entry. And with us at this moment is the man who is going to be watching all of that very, very carefully, John Kowal, who's the Orion Thermal Protection System Manager. John, your big moment is lying ahead here. The plunge back into the Earth's atmosphere. This is the moment of truth to test the heat shield. What kind of thermal environment are you expecting for Orion as it makes its way into the Earth's atmosphere and then back through the atmosphere itself?
Yeah, so, as you mentioned, 5,000 degrees on the ship, but to back that up, how do we get there? So that vehicle still has all that energy that the launch rocket put into it during that first beautiful launch, right? So that gets converted into velocity. So we're going at 25,000 miles per hour, which is, how do you even fathom what that means? It's 7 miles per second. Wow. So all that energy, enough to power 4,000, 5,000 homes in a day, we have to get rid of it. And how do we do that? The vehicle comes slamming into the atmosphere, starts trying to push the air up out of the way. That air is pushing back, the pressures go up, the temperatures go up. We're talking upwards of around 10,000 degrees Fahrenheit in the flow field. So that energy goes into the flow field, and then the flow field wants to give it back to the surface of the TPS. So that's what the TPS is going to see, or what the heat shield is going to see, and that's what pushes it up to 5,000 degrees Fahrenheit.
What kind of testing was required throughout the course of the preparations for Orion to prepare the vehicle for launch that made you confident that it could withstand the rigors of this sort of environment?
Yeah, there's been a lot of testing. I mean, we've been at this for since the end of the shuttle program. If you think back to that system, that was a reusable system, we had kind of been out of the business of these ablation materials for quite a while, since Apollo. So we had to train a whole new generation of engineers on developing that type of system, as well as getting the materials back. So there was a lot of testing in arc jets. That's the primary way that you test these types of materials. You can create these temperatures. It's like a wind tunnel with a lightning bolt going down the center of it, and that's how you create this high temperature plasma, and that gets impinged onto the test article. So we do a lot of materials testing. We've done quite a bit of testing of the system. You know, even though we're using the same material, the AVCoat that they used in Apollo, it's in a different form. And so we made it into blocks. Those blocks have seams that have to be filled. Those seams are always one of the areas that you want to test the most, is because that's where the problems happen. And so we've done a lot of testing there in the thermal, and also structurally. We've had to do a lot of testing to see how the AVCoat blocks interact with the structure underneath, and make sure that it's all going to hold up to those loads.
And John, it's about 11 minutes or so from the time of entry interface at an altitude of about 400,000 feet until we come out of that second blackout period. So that's going to be a very interesting time, a sort of a nail-biting time, if you will. But after the vehicle splashes down and is back at the Kennedy Space Center in a few weeks for post-flight analysis, what are the sorts of things that you and your engineering team will be looking for to give it a passing grade in preparation for putting a crew on board a couple of years from now?
Yeah, there's a couple things that we look at. I break it into two different categories. The first is the flight data. We have instrumentation embedded in the heat shield at a number of locations. So we measure temperatures, we measure heat rates, we measure pressures, stresses. All that data will tell us how the material actually performed in that flight environment. It will also help us to inform our computer modeling methods, and that's another thing that we need to make sure that it's performing how we thought it was going to perform, so that we can use those models in the future, you know, to predict for other missions. Now, the other thing we'll do is we'll be looking at the hardware itself. You know, the instrumentation, you only get measurements where you put that instrument, of course, right? But looking at the heat shield, just looking at it, the big picture, you can see the streamlines, you can see how the flow was going across the heat shield, you can see where boundary layer transition may have occurred. So there's so much to just visually see, and then we'll be taking samples of the heat shield, we'll be taking that material out and looking at how much had ablated, looking at the char thickness, the density gradients as you go through as the material burned off, and comparing that to what our models have predicted. And again, that'll help us to be able to validate and correlate our models further.
Very good. It's going to be a very important time for the engineers, of course, and we'll see how Orion fares here in the next hour or so. John Kowal, Orion's Thermal Protection System Manager, thanks very much for joining us this morning.
Thank you.
Now just 16 and a half minutes away from the separation of the crew module from the European service module. That will begin a trip hammer series of events as Orion begins the process of entering the Earth's atmosphere. Entry interface just 36 minutes away. So let's go back out to the Pacific Ocean west of Baja, where Daryl is on the USS Portland. Daryl?
That's right, Rob. A quick update for you on out here in the Pacific Ocean, just off the coast of Mexico. We have the small boats, the Navy small boats. All 6 boats are now in the water. They call them CRICs. These are Navy boats that are inflatable, highly maneuverable. These are the ones that will actually put hands on the spacecraft in order to secure it and eventually get it tied to lines that brings it to the back of the ship and into the well deck. I want to talk a little bit about this location here today. This location in the Pacific, we're just about 5 miles away from the splashdown area. This was actually the backup location. Initially, this was supposed to happen off the coast of San Diego, California, but the weather forecast for that area called for a cold front that has moved in today, bringing with it 12-foot high seas, and those seas would have been too high to perform this operation, too high for the small boats for recovery. So Recovery Director Melissa Jones and the mission management team made the decision to back up and go to the backup location 300 miles south of San Diego, and that's where we find ourselves today with excellent weather in order to do this operation. As you look off into the sky, we're awaiting the second to last weather balloon release that we will have for the day. This weather data critical to the operation that is happening today, especially when it comes to the landing point of the crew module in the ocean, as well as the debris that goes with it. And that debris happens during the separation of the forward bay cover, which covers the parachutes, and then of course the parachutes and their hardware themselves. All of it together, they take in the winds, and you can feel the winds are picking up a little bit. That wind data will give us refined information and data in order to calculate exactly the landing spot. Now, we're not alone out here in the Pacific Ocean. We do have friends helping us today, and I want to take a shot now of a ship off in the distance that has joined us for today's operation, and that is the USS Montgomery. That ship is just a few miles away. As you can see it there, the USS Montgomery is providing security today. It is what the Navy calls a littoral ship. It specializes in close-to-shore combat. It's highly maneuverable in that space. Today, though, it has a peaceful